Hello there and welcome to Life Beyond Seen, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, our gentle journey takes us to a stretch of water that has unsettled sailors, fascinated explorers, and kept scientists peering into screens, maps, and deep-sea instruments with a very specific mix of excitement and concern. We are drifting toward the Red Sea, a place whose name sounds dramatic enough already, but whose reality turns out to be far stranger than a title can manage on its own. At first glance, it may not seem like the sort of place that should inspire dread in people with advanced degrees and very expensive equipment. It is beautiful, warm, bright, and framed by desert. Holiday brochures would be delighted with it. Sunlight glitters on the surface. Coral reefs bloom in extraordinary colours. Fish slip through the water like they know something the rest of us do not. From above, it can look serene, even inviting, as though nature had decided to put together one of its more polished displays and keep the rough edges out of sight. And yet, beneath that surface lies one of the most unsettling marine environments on Earth. Scientists are not frightened of it in the sense of dropping their clipboards and running away in sandals, though to be fair, some of them might consider it on difficult days. What unsettles them is the way the Red Sea refuses to behave like an ordinary sea. It is too hot in places, too salty in others, too geologically active, too biologically unusual, and too full of clues about how oceans change when a planet starts pushing its limits. It is the kind of place where the water itself can become part of the warning. Before we settle into all of that, I would love for you to take a quiet moment and notice where you are right now. Where are you listening from tonight? Is it late where you are, or only just becoming evening? Perhaps you're under a blanket. Perhaps you're staring at the ceiling. Perhaps you're pretending you're only listening for 5 minutes and already suspecting that 5 minutes may have slightly different plans. In any case, I am glad you are here. If you find this soothing, interesting, or simply a nice way to let your mind drift somewhere unusual for a while, I would be very grateful if you gave the video a like and maybe subscribed. It helps this calm little corner reach more people who might want something thoughtful to listen to when the day is winding down and the world outside feels a bit too loud. Now, I will do my best not to make the Red Sea sound so alarming that you end up wide awake with a newfound distrust of coastlines, but if that does happen, at least you will know exactly why a body of water can make even seasoned researchers pause and say, well, that is not ideal. So, settle in, ease your shoulders, and let us begin with a simple idea. There are places on Earth that feel ordinary until you look closely. Then there are places that become less ordinary with every new layer you peel back. The Red Sea belongs firmly in the second group. It sits between northeastern Africa and the Arabian Peninsula, forming a long, narrow basin that has mattered to human beings for thousands of years. Traders crossed it, empires watched it, pilgrims travelled beside it, armies measured it, myths collected around it, history moved through it, and modern shipping still depends on it. It is not tucked away in some remote corner of the planet, where only a handful of specialists ever visit. It is one of the world's most strategically important stretches of water. Enormous volumes of trade pass through it. Nations border it. Tourists dive into it. And because it is so visible, so used, and so present in human affairs, there is something especially unnerving about how much of it remains difficult to fully understand. That difficulty begins with contrast. The Red Sea is both familiar and extreme. Its shores are dry and stark. Its shallows can be dazzlingly clear. Its reefs are among the most resilient on Earth. But drop far enough below the surface and the rules begin to change. Some parts of its deep basin contain pools of super salty water so dense that they sit on the seafloor like underwater lakes. Not figuratively, not in the poetic, oh how mysterious sense. They're real heavy brine pools layered beneath normal seawater, so hostile to most life that creatures drifting into them can be stunned or killed. Imagine a sea with secret pockets inside it, where chemistry becomes a trap. Scientists looked at that and, quite reasonably, decided it deserved attention. Then, there is the heat. Much of the Red Sea is already warmer than many other marine environments, and that matters because scientists increasingly study it as a natural laboratory for the future of the world's oceans. Coral reefs elsewhere often bleach and collapse under rising temperatures. Some Red Sea corals, especially in the northern part, seem unusually tolerant of heat. That makes the region valuable, but also unsettling. It is not just a place to admire, it is a preview screen. When researchers look at the Red Sea, they are often not only asking what is happening there now, they are also asking what its conditions might tell us about seas elsewhere as climate pressure intensifies. A place stops feeling merely exotic when it starts behaving like a message. Still, that only covers the water itself. The seafloor has its own plans. The Red Sea lies along a rift, a place where the Earth's crust is being pulled apart. Very slowly, very steadily, the African and Arabian tectonic plates are separating. The Red Sea is not just a basin full of water, it is part of an active geological process. In a sense, it is a young ocean in the making, caught in the act of forming. That alone would be enough to interest geologists, but interest is not the same thing as comfort. When a landscape is still being built by tectonic tension, volcanism, and deep structural change, surprises become part of the job description. The ground below is not as settled as one might like. This is one reason the Red Sea keeps drawing teams back. Oceanographers, marine biologists, geologists, climate researchers, chemists and engineers all come to it with their own instruments and questions, and the sea has a habit of answering in ways that lead to more questions. A deep basin that should have one set of characteristics reveals another. A microbial community turns out to be surviving in conditions once thought too harsh. A hidden pool preserves sediment records that help reconstruct ancient climate. A reef shows signs of unusual resilience, but only under conditions that may not hold forever. Every answer comes with a small administrative fee paid in uncertainty. If you think about it, that may be one of the most reliable ways to unsettle a scientist. Not with a single dramatic monster from the depths, though I admit that would simplify the paperwork, but with a system that keeps resisting neat explanations. Scientists, despite the stereotype, do not expect the world to be tidy. They know it is messy. They know nature loves exceptions. But they do like patterns they can test, models they can refine, and mechanisms they can trace with some confidence. The Red Sea offers all of that, and then quietly adds extra complications, like a waiter placing another mysterious dish on the table after you are certain you had ordered enough. Its salinity, for example, is unusually high. Because the region is hot and dry, evaporation is intense. At the same time, there's very little rainfall and almost no major river input to dilute the salt. Water enters through the narrow Bab el-Mandeb Strait to the south, but the exchange is limited compared with more open ocean basins. Over time, this creates conditions that are tough on marine life and physically unusual by global standards. Many organisms can survive only within fairly stable ranges of temperature, oxygen, acidity, and salinity. The Red Sea often asks them to make an effort. Some do more than survive. They adapt. That is part of what makes the region scientifically valuable. Life there can reveal how organisms cope with environmental extremes. Microbes in the Red Sea, especially those associated with brine pools and hydrothermal activity, may hold clues about biochemical survival in conditions that resemble ancient Earth or even hypothetical extraterrestrial environments. That is the sort of sentence scientists say with great caution, and everyone else hears as, "So there are weird microscopic things down there doing impossible chemistry," which in fairness is not entirely wrong. The brine pools deserve a little more attention because they are among the features that most directly feed the Red Sea's unsettling reputation. These pools form when highly saline water collects in deep depressions on the sea floor. Because that water is denser than the surrounding seawater, it does not mix easily. It settles. It stays. It creates sharply defined boundaries. In some of these zones, oxygen is nearly absent. Temperatures can be elevated. Chemical concentrations can be extreme. Sediments accumulate with relatively little disturbance. preserving information about past environmental conditions. For scientists, this is extraordinary. For anyone imagining a casual swim, it is a firm reminder to remain in the shallows and make better life choices. What makes these pools especially eerie is the way they behave almost like separate worlds. A remotely operated vehicle can move through normal seawater and then approach a brine interface that looks uncannily like a shoreline under the sea. The visual effect is strange enough. The chemical difference is even stranger. Fish and other animals approaching too closely can become disoriented. Some predators have learned to linger near the edges, taking advantage of prey that wander into trouble. Nature, as ever, is capable of inventing hunting strategies that would seem rude if copied in an office environment. And yet the fear scientists feel is not simple fear of danger. It is closer to respect edged with concern. The Red Sea is dangerous in the way a complex machine is dangerous when it is still running while you're trying to understand how it works. It is active. It is layered. It is influenced by deep earth processes, atmospheric heat, ocean circulation, extreme chemistry, and ecological adaptation all at once. A change in one part of the system can affect another. Studying it means working across disciplines, which sounds very elegant until you remember it also means every expert brings a different list of things that could go wrong. There is also the matter of scale. Human beings are quite good at underestimating seas. We stand at a shore, see a horizon, and feel as though we have taken the measure of something. The Red Sea especially invites that mistake because it is narrow compared with open oceans and bounded by land that feels close enough to define it. But narrow does not mean simple. In some areas it plunges to great depths. It contains steep gradients, isolated basins and hidden environments. It is less like a tidy channel, and more like a long corridor with locked doors, half the lights off, and a basement someone forgot to mention in the brochure. That same corridor connects worlds. Through the Suez Canal at the north and the Bab el-Mandeb at the south, the Red Sea sits in a position that makes it ecologically and economically significant. Species move through it. Ships rely on it. Political tensions brush against it. Environmental changes within it can ripple outward. This is another reason scientists pay attention with such intensity. A strange sea in an isolated location would matter to specialists. A strange sea tied to global trade, biodiversity shifts, and regional stability matters to everyone, even if most people do not realise they are depending on it while ordering socks online at midnight. Over the years, the Red Sea has also accumulated a certain reputation because of the gap between what people expect and what researchers find. People hear sea and imagine waves, reefs, fish, perhaps a slightly overexcited holidaymaker with rented snorkeling gear. Scientists go down with sensors and sediment cores and start reporting superheated brines, tectonic stretching, volcanic islands, low oxygen zones, unusual coral resilience, microbial extremophils, and environmental warning signs. One of those pictures feels like a travel ad. The other feels like the opening pages of a report nobody writes unless they are trying very hard not to sound alarmed. And perhaps that is the right mood to bring into this. Not panic, not melodrama, not the idea that the Red Sea is cursed, haunted, or personally offended by marine science. It is not a villain. It is a place where natural processes meet in unusually intense ways. That intensity is what makes it so useful and so unnerving. Scientists are drawn to it because it can reveal how oceans behave under stress, how life adapts to chemical extremes, how tectonic boundaries evolve, and how climate pressure reshapes marine systems. They are unsettled by it because each of those topics is already serious on its own, and the Red Sea insists on offering all of them at once. When you put it that way, the fear makes sense. It is the fear of seeing too much at one site, the fear of recognizing patterns that may become more common elsewhere, the fear that a beautiful place can also be an early warning system. Scientists are not standing at the edge of the Red Sea trembling because they believe the water might lunge at them like an offended cat. They are unsettled because it has become one of those rare environments where the future seems to arrive a little early. That future can appear in different forms. In one conversation, it is coral survival in hot water, and the question of whether that resilience can teach us something valuable. In another, it is the spread of marine heat stress, and what happens when ecosystems are pushed too far. It might be a discussion of deep brine chemistry, or it might be a concern about coastal development, pollution, shipping pressure, invasive species movement, or changing circulation patterns. The Red Sea keeps offering both wonder and warning in the same frame, and human beings are not always comfortable looking at both together. There is something else worth noting before we move deeper. Fear in science is often a sign that people have started to understand the stakes. A place is not frightening simply because it is unknown. The unknown can be exciting. It becomes frightening when enough is known to reveal how much remains difficult, delicate, or potentially consequential. The Red Sea has crossed that threshold. We know enough about it now to grasp that it is extraordinary. We also know enough to realise that its extremes are not just local curiosities. They connect to bigger questions about oceans, climate, geology, and survival. That is why, even after decades of study, it continues to trouble people who make a career out of asking careful questions. Its reefs are beautiful, but beauty is not the story. Its depth is impressive, but depth is not the story either. The real story is that the Red Sea combines heat, salt, tectonic change, chemical oddities, biological adaptation, and strategic importance in one restless system. It is a body of water that looks manageable until you start listing what is happening beneath and around it. Then it becomes the sort of place that can keep research teams busy for years and still leave them saying, with admirable understatement, that more work is needed. And more work is always needed, because once you begin with a place like this, one question leads to another. You start with a sea and end up talking about the Earth's crust pulling apart. You start with coral and end up confronting the future of marine ecosystems. You start with unusual water chemistry and find yourself staring at deep basins where whole microbial communities are thriving under conditions that would seem almost designed to discourage guests. Piece by piece, the Red Sea stops being a destination and starts becoming a case study in how unsettling the natural world can be when it is functioning exactly as it intends to. So, now that we have eased our way to the shoreline and let the broader picture settle into place, we can move into the long human relationship with this water, because the Red Sea did not begin terrifying scientists when modern instruments arrived. Long before remotely operated vehicles, satellite maps, and temperature sensors, this sea was already earning a reputation for swallowing certainty, challenging travellers, and reminding anyone who crossed it that appearances can be extremely misleading, which is where the next part of the journey begins. The Red Sea has unsettled people for far longer than scientists have had sonar, submersibles, and carefully labelled storage tubes. Long before marine geologists lowered instruments into its depths, long before biologists sampled its reefs and chemists studied its strange deep water layers, this narrow body of water had already earned a reputation as a place where plans could unravel very quickly. It sat at the meeting point of continents, deserts, kingdoms, religions, trade routes, and ambitions. It looked like a passage. It behaved very often like a test. That has much to do with geography, which can sound terribly dry until geography starts deciding the fate of empires. The Red Sea lies between northeastern Africa and the Arabian Peninsula, stretching for well over 1,000 miles in a long, narrow shape that seems almost designed to tempt people into underestimating it. On a map, it can appear manageable. It is not one of the vast, open oceans. It does not sprawl endlessly across the globe. It is bordered by land on both sides, which gives the impression of a route that can be understood, controlled, and used. Human beings are very fond of seeing a strip of water between two shores and thinking, that looks convenient. History is full of examples suggesting we should maybe stop doing that. Because the Red Sea has always been more than a strip of water. It has been a corridor, a barrier, a prize, a hazard, and a lifeline. It linked the Mediterranean world, the Arabian Peninsula, East Africa, and the Indian Ocean trade networks beyond. Goods moved through it. Ideas moved through it. Armies hoped to move through it efficiently, and often discovered that efficiently is one of those words that sounds better on parchment than it feels in practice. Wind, reef, current, heat, and distance had a way of reminding commanders, merchants, and rulers that a line on a map is not the same thing as mastery. One of the simplest reasons the Red Sea could swallow certainty is that certainty loves straight lines, and the Red Sea does not really cooperate with them. Its coasts are irregular, its winds can be stubborn. Navigation through reef-fringed waters demands attention. Safe harbours matter. Timing matters. Local knowledge matters. Even in periods when maritime technology improved, there remained a stubborn truth that anyone crossing or controlling the sea needed more than ambition. They needed information, patience, and a willingness to accept that nature might veto their timetable. Empires, as it turns out, are not always naturally gifted at patience. The ancient Egyptians knew the region mattered. Their power was tied to the Nile, but they were not blind to the strategic value of routes leading eastward and southward. Expeditions were sent toward the Red Sea coast for trade and resource gathering. Among the most famous destinations associated with Egyptian seafaring was the land of Punt, still debated in some details by scholars, but broadly understood as a source of luxury goods such as incense, ebony, gold, exotic animals, and other prized items. Reaching such places required organisation and effort. Ships had to be built or disassembled and carried across desert routes to the coast, then launched into waters that were useful but not forgiving. Already, very early in recorded history, the Red Sea was not merely scenery. It was a logistical problem with commercial benefits attached. That combination tends to attract states. If a route is dangerous but profitable, some ruler sooner or later decides it should be theirs. Control over Red Sea access could strengthen trade, expand influence, and tie distant regions together. It could also drain resources, expose weaknesses, and create the deeply irritating situation in which a sea route that looked profitable in theory turned out to be expensive in practice. Ports mattered enormously. So did inland connections to those ports. No one simply controlled the Red Sea by pointing at it and declaring confidence. They needed supply lines, naval capacity, diplomatic ties, and the ability to cope with local realities that had often been shaped by communities living there far longer than any empire's latest strategic memo. The Romans understood this quite well. By the time Rome turned serious attention toward the Red Sea and Indian Ocean trade, maritime commerce linking the Mediterranean world to Arabia, East Africa, and India had become increasingly important. Goods like spices, perfumes, textiles, precious stones, and luxury items moved through these routes with considerable profit attached. Roman Egypt, particularly after Augustus brought it under imperial control, became a major gateway for this commerce. Ports on the Egyptian Red Sea coast, such as Berenike and Myos Hormos, were connected by desert roads to the Nile, allowing cargo to move onward to the Mediterranean. It was a sophisticated system. It was also fragile in all the ways that expensive systems tend to be when they depend on weather, labour, security, and distances large enough to make every mistake memorable. Roman merchants and navigators learned to use monsoon winds in the Indian Ocean, which greatly shaped trade patterns. That knowledge expanded commercial possibilities, but it did not make the Red Sea easy. Ships entering or leaving had to cope with narrow passages, reefs, seasonal conditions, and the broader challenge of operating in a region where local expertise could mean the difference between profit and disaster. It is one thing to build a global empire. It is another to persuade the wind, coral formations, and navigational hazards to respect your administrative structure. Rome achieved many things. It did not, in the end, persuade coral to become more accommodating. There is something almost comical about how often powerful states assume difficulty can be solved by declaring a place important. The Red Sea has always resisted that. Importance only increased the number of people trying to use it. It did not flatten the reefs or calm the weather. This perhaps is one reason it swallowed certainty so effectively. It punished the belief that strategic value automatically produces strategic control. A ruler might understand the Red Sea mattered enormously and still fail to handle it properly. History is generous in providing examples of this principle across many regions, but the Red Sea offered an especially sharp tutorial because its narrowness encouraged overconfidence. People could see the opposite shore. This did not mean the crossing would behave. As centuries passed, different powers emerged around its coasts and approaches. Arabian, African, Mediterranean, and later Islamic polities all recognized its significance. With the spread of Islam in the 7th century, the Red Sea gained even greater religious, political, and commercial importance. It was tied to the holy cities of the Arabian Peninsula, to pilgrimage routes, and to the economic systems of expanding Muslim states. Ports along the Red Sea became vital nodes in networks that linked Egypt, the Hijaz, Yemen, the Horn of Africa, and beyond. Again, the sea acted both as connector and obstacle. It brought regions together. It also reminded them that connection required skill. Trade across the Red Sea and through its linked routes carried not only goods, but people and ideas. Merchants, scholars, pilgrims, sailors, and administrators moved along corridors shaped by both land and sea. Languages met there, legal systems met there, religious traditions met there. That kind of contact can enrich societies tremendously, but it can also expose them to rivalry and instability. A strategic sea is rarely allowed to remain merely useful. Sooner or later, somebody wants exclusive advantage. Somebody else objects. The Red Sea, located where Africa and Arabia face one another at close range, was especially prone to this. It invited cooperation when conditions favoured it, and conflict when ambitions outpaced practicality. The medieval and early modern periods saw regional and external powers competing over Red Sea influence with considerable energy. The Mamluks of Egypt, for example, had strong reasons to care deeply about the Red Sea. Their interests included trade, defence, and the protection of pilgrimage routes. Later, the Ottoman Empire also recognised the region's importance, especially as Portuguese maritime expansion into the Indian Ocean threatened existing trade systems and political balances. Suddenly, the Red Sea was not just a regional artery. It was part of a broader contest involving oceanic power, commercial monopoly, and imperial competition stretching from the Mediterranean to the Indian Ocean and beyond. The arrival of the Portuguese in the Indian Ocean at the end of the 15th century was particularly disruptive. By seeking to control maritime trade routes around the Cape of Good Hope and into the Indian Ocean, they challenged long-standing systems that had linked the Red Sea, the Arabian Sea, and the wider Eastern trade world. The Portuguese understood that if they could choke off or dominate key routes, they could redirect wealth and weaken their rivals. The Red Sea, therefore, became part of a major strategic calculation. Yet even aggressive naval powers with global ambitions found that dominating these waters was easier to imagine than to achieve. Local resistance, logistical difficulty, and the complexity of regional politics limited what outside powers could do. This is where the idea of the sea-splitting empires becomes more than a dramatic phrase. The Red Sea did not literally take a knife to maps and slice states in half, though history occasionally behaved as if it had considered the option. What it did do was expose the limits of imperial reach. Large states often depend on smooth communication between centre and periphery. They need troops, messages, goods, officials, and revenue to move in a reasonably reliable way. The Red Sea offered opportunities for that movement, but it also created bottlenecks, vulnerabilities, and dependencies. Whoever controlled its ports and crossings gained leverage. Whoever failed to secure them found that the sea could become a dividing line between intention and execution. Geography contributed strongly to that leverage. At the southern entrance lies the Bab el-Mandeb Strait, a name often translated as the Gate of Tears, which is not exactly the sort of branding that says, "Welcome, this will be straightforward." Even without indulging in melodrama, it is fair to say the strait has long been recognised as a place of risk and consequence. Narrow maritime choke points matter because they concentrate traffic and expose it to control, disruption, weather and conflict. When goods, fleets or pilgrims must pass through a constrained route, that route becomes strategically sensitive. Control over such passages can enrich states, provoke wars, and encourage all sorts of grand statements from leaders who are still privately hoping the currents will cooperate. At the northern end, the Red Sea's connection to the Mediterranean would eventually be transformed by one of the most consequential engineering projects in modern history, the Suez Canal. Before its construction in the 19th century, goods moving between the Mediterranean and the Red Sea often depended on overland routes across Egypt. The canal changed global trade by creating a direct maritime passage between Europe and Asian waters. It also dramatically increased the geopolitical importance of the Red Sea. What had always been significant became indispensable. The sea now formed part of one of the world's great commercial arteries, a corridor through which global trade could move more quickly and efficiently than by sailing around Africa. That efficiency, of course, came with a familiar side effect. It made the region even more contested. The canal and the Red Sea route became central to imperial strategy, especially for Britain, whose global system depended heavily on rapid maritime communication with India and other territories. Control over Egypt, influence in the Red Sea, naval presence in adjacent waters, and the security of coaling stations and ports all became deeply important. Once again, a sea that appeared on maps as a route was in practice a chain of dependencies. Protecting it required fleets, diplomacy, fortifications, commercial agreements, and constant vigilance. The more the world relied on the route, the less room there was for mistakes. The Red Sea's role in imperial competition became painfully clear during crises and wars. In the age of steam, telegraph cables, colonial rivalry, and later oil transport, it was not enough for a power to admire the Red Sea's strategic value. It had to secure it. Rival empires probed its edges. Local uprisings affected access. Shifts in the Ottoman Empire, European colonial expansion, and later 20th century decolonisation all changed the political landscape around its shores. Through all of this, the sea remained what it had always been: useful, difficult, and impossible to detach from the lands and people surrounding it. This point matters because seas do not operate in isolation from coasts. The Red Sea's history is also the history of Egypt, Sudan, Eritrea, Djibouti, Saudi Arabia, Yemen, Jordan, and Israel, as well as earlier polities and communities whose names appear and disappear across the centuries. Ports rose and declined. Some were enriched by trade. Others were damaged by war, disease, silting, political change, or shifting commercial routes. Coastal communities developed intimate knowledge of local winds, anchorages, fishing grounds, and reef systems. Imperial planners often needed that knowledge, even when they preferred to imagine that central authority alone was sufficient. This is one of the quieter ways certainty gets swallowed. Local reality does not always care about official confidence. You can see this in military history as well. Campaigns conducted near or across the Red Sea frequently ran into the old problems of supply, terrain, and communication. A commander might plan movement along the coast or across nearby deserts and discover that moving men, animals, food, water, and equipment in intense heat is a rather unkind exercise. Navies could support campaigns, but only if their own access and logistics held up. Ports could serve as lifelines, but only if they were secure and adequately provisioned. The sea gave options. It also multiplied the number of ways a plan could go wrong. Armies are often very confident before they meet a difficult environment. They're usually less confident after. There is another reason the Red Sea repeatedly unsettled large powers. It sat at the intersection of maritime and desert systems. That means control of the water alone was rarely enough. Inland routes mattered. Caravans mattered, oases mattered, tribal alliances mattered, Religious legitimacy mattered. Whoever hoped to dominate the Red Sea had to think in more than one direction at once. It was not merely a naval theatre or merely a land frontier, it was both. This hybrid character made it hard to reduce to a single formula of control. An empire strong at sea might struggle on land. A power dominant inland might lack maritime capacity. The Red Sea rewarded flexibility and punished one-dimensional thinking, which is awkward because empires do enjoy one-dimensional thinking when it comes attached to uniforms and official stamps. By the 19th and 20th centuries, technological change altered the scale of activity in and around the Red Sea, but not the underlying pattern. Steamships reduced dependence on wind. The Suez Canal increased traffic. Modern weapons increased the stakes of controlling choke points. Oil later transformed global maritime priorities. The Red Sea became even more central to world economics and strategy. Yet vulnerability remained built into the system. Close the canal, threaten the strait, destabilize key coasts, or turn adjacent regions into conflict zones, and suddenly the world is reminded how much it relies on this narrow corridor. For all the sophistication of modern logistics, there is still something almost medieval about the fact that enormous global systems can be troubled by a difficult passage between two stretches of land. Events in the 20th century made this plain. Wars in the Middle East, including the Arab-Israeli conflicts, repeatedly affected access to the Suez Canal and the wider route. The canal's closure after the 1967 war had enormous consequences for shipping, trade patterns and naval strategy. Tankers and cargo ships had to reroute around the Cape of Good Hope, adding time and expense. The shock was not merely regional, it was global. An entire commercial system felt the weight of one blocked corridor. Once more, the Red Sea and its northern gateway demonstrated that when this route is compromised, confidence in smooth international movement evaporates faster than one would prefer. The phrase "swallowed certainty" fits especially well here because the Red Sea has repeatedly revealed how dependent great powers are on assumptions they barely notice until those assumptions fail. Assumptions about secure transit, assumptions about reliable access, assumptions about technological superiority solving geographic difficulty, assumptions about the ability of large states to impose order on complex local conditions. The Red Sea did not necessarily destroy empires on its own. Few places do, but it helped expose cracks. It turned strategic miscalculation into material cost. It reminded ambitious states that between intention and success there may be reefs, straits, winds, political rivals, and a deeply inconvenient amount of reality. There is also the human scale of uncertainty, which matters just as much as imperial strategy. For ordinary sailors, merchants and pilgrims, the Red Sea was not an abstract route on a minister's desk. It was heat, thirst, cramped decks, unfamiliar coasts, hidden hazards, and the constant possibility that a journey might not go as expected. Navigation in reef-filled waters requires concentration even today. In earlier periods, with less precise instruments and charts, the margin for error could be painfully narrow. Illness could spread on ships, supplies could run low, storms or contrary winds could delay travel. Water could become scarce. It is easy to talk about sea routes in grand historical terms. It is harder and more accurate to remember that these routes were lived one anxious day at a time by people who had every reason to respect the water. Pilgrimage offers a particularly revealing example. For many Muslims travelling toward the holy cities, Red Sea routes became essential at different times and from different regions. These journeys were spiritually significant, but they were also materially demanding. Ships, ports, and overland transitions had to function well enough to carry large numbers of people. Disease outbreaks, piracy, conflict, weather, and administrative failure could all turn a sacred journey into a harsh ordeal. The Red Sea, in that sense, did what it always does. It connected the faithful to a destination while insisting that connection never be taken for granted. The same basic truth applies to commerce. Wealth moved through the Red Sea for centuries, But every bale of cloth, sack of spice, load of grain, amphora of wine, chest of coins, and later barrel of oil depended on systems that could fail. Ports could be attacked, ships could be delayed, markets could shift, rulers could overtax, rivals could interfere, climate could alter conditions. The sea was not simply a neutral medium through which trade passed. It was an active part of the calculation, imposing constraints and risks that shaped prices, schedules, and strategy. Economies built around such routes could flourish impressively. They could also wobble when the route became unstable. In all of this, the Red Sea gathered a peculiar kind of historical weight. It became one of those places where the ambitions of the very large meet the realities of the very specific. A ruler might dream in continental terms, but the dream still had to pass through a narrow strait, a reef-lined channel, a desert road to a port, or a coast held by someone else. This is not merely a historical curiosity. It helps explain why scientists today inherit a landscape already thick with caution. When they arrive with research vessels and instruments, they are not entering a blank stage. They are entering a sea with a long record of reminding people that confidence is fragile. That long record also matters because it shaped the stories people told about the region. Seas that repeatedly disrupt plans do not remain merely geographic. They become moralized, dramatized, mythologized, and remembered in ways that emphasize uncertainty. The Red Sea appears in religious tradition, historical writing, travel accounts, strategic thinking, and popular imagination. It is associated with crossing, escape, danger, trade, revelation, and control. That accumulation of meaning does not tell us the chemistry of deep brine pools or the heat tolerance of coral reefs, but it does create a background hum of seriousness. Even before science discovered the full extent of the sea's physical strangeness, human history had already labelled it a place where things happen that are larger than expected. And perhaps that is why the transition from history to science feels so natural here. The same sea that once unsettled merchants and emperors now unsettles geologists and marine biologists, not because the old stories were secretly scientific reports, but because the underlying pattern is similar. The Red Sea keeps confronting people with complexity that exceeds the simple version of the map. In one age, that complexity was naval, commercial, religious, or imperial. In another, it became tectonic, chemical, ecological, and climatic. The language changed. The discomfort remained. By the time modern science turned its attention more deeply to the Red Sea, it was already dealing with a place that had tested control for millennia. What researchers found beneath the surface did not contradict that older history. It deepened it. The sea had always been strategically difficult. Now it turned out to be physically and biologically unusual as well. It had always shaped empires by controlling movement and exposing vulnerability. Now it was revealing hidden systems that could reshape how we understand extreme marine environments. In that sense, the Red Sea did not stop swallowing certainty when the age of empire faded. It simply found a new audience with more instruments and in some cases more elegant vocabulary for saying, "This is stranger than we expected," which leads directly into what lies beneath the surface, where the unsettling part becomes much less historical and much more immediate. And that leads directly into the part of the Red Sea that tends to make scientists stop speaking in broad, confident summaries and start speaking in very careful specifics. Because once you move below the bright surface, past the reefs, past the fish, past the warm upper layers that make the sea seem almost welcoming, you arrive at a set of conditions that sound less like a normal marine environment and more like a place assembled from several bad ideas at once. The Red Sea is already unusual at the surface, but the real shock begins in its deep basins, where the water can become so salty, so hot, so low in oxygen, and so chemically strange that researchers describe it as one of the most extreme habitable environments on Earth. One reason this feels so wrong at first is that most of us carry around a simple picture of the deep sea. We imagine darkness, cold, pressure, and a great deal of quiet. That picture is not completely inaccurate for much of the world's ocean, but the Red Sea has never been terribly interested in behaving like much of the world's ocean. It is already a marine basin with unusual physical and chemical conditions, and it is among the least explored marine environments despite its importance. Its waters stay warm compared with many other seas, and the basin contains a wide variation of ecological niches, including some that are extreme enough to make even veteran researchers sound slightly stunned when they describe them. The first surprise is geological. The Red Sea is not just a container for water, it is part of an active rift system formed by the separation of the African and Arabian plates. That stretching has produced a deep axial depression running through the basin. In simple terms, the seafloor here is not settled and finished. It is part of a place where the crust is being pulled apart, where heat flow matters, where fluids move through rock, and where the structure of the basin helps create pockets of extraordinary conditions. After roughly half a century of study, scientists have identified about 25 deep-sea brine pools in this rift-related depression, with several of the best studied, including Atlantis, Too Deep, Discovery Deep, and Keybrit, lying below about 1.5 kilometres of water. A brine pool sounds almost harmless until you remember that brine is a very polite word for water that has become alarmingly salty. In the Red Sea's deeps, these pools collect in seabed depressions as dense hypersaline liquids that barely mix with the surrounding seawater. Their rarity alone would make them worth attention. Even worldwide, only a few tens of deep-sea brine pools are known across the Red Sea, the Mediterranean, and the Gulf of Mexico. But the Red Sea has the highest number of them, and their origin is generally tied to the dissolution of buried evaporates, together with the basin's tectonic and hydrothermal history. What this means in practice is that the seafloor can contain isolated, heavy bodies of water that sit there like submerged chemical traps, each with its own harsh internal rules. Then comes the part that really unsettles people. Some of these pools are not only hypersaline, they're also anoxic, acidic, metal-rich and hot. Atlantis Too Deep, the most famous of them, has long been known as the largest and best characterised hot brine system in the Red Sea. It lies at roughly 2,200 metres depth and has been measured with temperatures reaching 68.3 degrees Celsius in its hottest layers. Discovery Deep, nearby, is cooler by comparison, which is a slightly absurd sentence because cooler in this case still means around 45 degrees Celsius in parts of the brine. These were the first hydrothermal sites discovered in the oceans, and scientists have monitored them for decades because their temperatures, layering and chemistry are so unusual. Most of us would not describe near boiling salty metal-rich deep water as a promising neighbourhood. Microbes, on the other hand, have apparently chosen to keep an open mind. That is where the Red Sea begins to feel less like a normal sea and more like a collection of separate worlds stacked on top of one another. Above the brine sits ordinary seawater by comparison. Below or within the brine, conditions shift sharply. The boundary between these water masses can be so stable because of the density difference that it acts almost like a physical division. Oxygen drops away, salinity shoots up, pH can fall, temperature can rise, metal concentrations increase. Many larger bottom-dwelling animals that would normally churn and disturb seafloor sediment are excluded by the anoxia. The result is a place where ordinary deep-sea life may struggle, but specialised microbes flourish, and where the absence of burrowing megafauna allows sediment layers to remain remarkably intact. For a geologist, that is invaluable. For a fish with poor judgment, it is probably the end of a very bad afternoon. The preserved sediments are one of the main reasons scientists find these pools so compelling. In the Gulf of Aqaba, researchers reported the neon brine pools in 2022, including one main pool of about 10,000 square metres and three much smaller ones. Because anoxia keeps out the usual sediment-disturbing animals, the pool preserves a clean stratigraphic record. In that study, the preserved sequence spanned at least 1,200 years and captured evidence linked to flash floods, local seismicity, and tsunami-related terrestrial sediment. In other words, these strange underwater basins do not merely sit there being chemically aggressive, they also work like archives, storing a layered history of climatic and tectonic events. It is difficult to overstate how useful that is. It is also difficult not to notice that one of the best archives of regional hazard history happens to be located in a place that looks like it was designed by someone determined to discourage visitors. There is also the biological side, and this is where the phrase, "a world that should not exist," starts to feel less like drama and more like a practical reaction. The Red Sea brine pools host rich microbial communities despite, or rather because of, their brutal chemistry. Reviews of the system describe these habitats as the most extreme niches in the Red Sea in terms of salinity, temperature and metal content, yet they support bacterial and archaeal communities adapted to exactly those stresses. Novel halophiles have been identified in places like Kebrit Deep, thriving under anaerobic hypersaline conditions. This matters because such organisms do not merely survive there, they perform chemistry there. They build metabolisms around conditions that would destroy most life forms we are used to imagining. When microbiologists study them, they are not simply cataloguing weird residents. They are mapping the outer limits of what life can do. That outer limit has attracted attention well beyond marine biology. Because these brine pools combine hypersalinity, anoxia, low pH, heat, and unusual chemistry, researchers treat them as analog environments for early Earth, and as guides in the search for life beyond Earth. That does not mean scientists think the bottom of the Red Sea contains a secret alien suburb. It means the rules that allow microbes to function there may resemble rules that mattered on the young Earth, or that could matter in other worlds with liquid water, chemical gradients, and hostile conditions. The same studies have also emphasized that microbes from Red Sea brine pools can produce useful enzymes and bioactive compounds, including molecules with antibacterial or anti-cancer potential. It is a neat scientific arrangement, really. The environment says this should be impossible, and the microbes respond by inventing tools industry and medicine would quite like to borrow. And then there is Atlantis 2 Deep, which manages to become even stranger once you look below the water itself. The basin is covered by layered metalliferous sediments, and multiple sources describe it as the largest present-day ore-forming environment or the largest known hydrothermal ore deposit on the ocean floor. That is a remarkable sentence to attach to an already extreme brine pool. The hydrothermal fluids and brines there are enriched in metals such as zinc, copper and cobalt at concentrations far above normal seawater. So the picture becomes more complicated again. This is not merely a hot, salty pit with unusual microbes. It is also an active mineral-forming environment, a modern example of processes that help scientists understand orgenesis and seafloor hydrothermal systems. The deeper one looks, the less the Red Sea resembles a finished marine landscape, and the more it resembles a laboratory still running its own experiments. That is one of the reasons the deep Red Sea makes scientists uneasy in a very specific way. It breaks the comfortable habit of putting natural systems into tidy categories. A sea should not also feel like a tectonic rift lesson, a hydrothermal site, a sediment archive, an extremophile habitat, and a warning about environmental limits all at once. But the Red Sea insists on doing exactly that. It is warm when many deep seas are cold. It is chemically aggressive where many marine settings are comparatively stable. It contains isolated brines, where one expects only water columns that mix more freely. It preserves records where ordinary seafloor life would normally stir the layers into confusion. Each feature is striking on its own. Together, they create the uneasy impression that one basin has been given too many jobs. There is also a psychological reason these places feel wrong, and it has to do with contrast. The Red Sea surface can be dazzlingly clear, full of reefs, tourists, dive boats, and perfectly ordinary marine beauty. Then, more than a kilometre below, the same basin contains brine pools with no oxygen, low pH, strange microbial mats, and temperatures hot enough to sound like a typing error. Scientists are trained to expect variation, Even so, there is something unsettling about how abruptly the Red Sea moves from postcard to nightmare fuel once you go deep enough. It is like discovering that beneath a very pleasant hotel lobby, there is a basement full of boiling salt, toxic chemistry, and microorganisms quietly thriving, as though none of this should concern them at all. The microbes, to their credit, are not being dramatic about it. The rest of us are doing enough on their behalf. The discovery history only adds to that mood. Anomalously high temperatures near the Red Sea seafloor were noticed in the mid-20th century, and by the 1960s the Atlantis II and Discovery brines had been confirmed and systematically investigated. Their temperatures continued to change over time, especially in Atlantis II Deep, where long-term measurements showed further warming in the convective layers. Even after decades of work, researchers were still finding new structures and new brine systems, including the Gulf of Aqaba pools reported in 2022. That means the scientific story here is not a tidy case of, we found the strange thing, explained it, and moved on. It is a continuing process in which the basin keeps producing fresh examples of its own extremity. There are few things more effective at unsettling researchers than a site that remains surprising after years of instrumentation, modelling, and repeat visits. So when people say the deep Red Sea contains a world that should not exist, what they usually mean is not that the laws of physics have failed, but that the place violates our everyday expectations about what a sea is supposed to be. We expect a body of water. The Red Sea offers water, certainly, but also layered brines, hydrothermal heat, preserved hazard history, rare chemistry, concentrated metals, and communities of organisms that have adapted to conditions most life would find intolerable. It is a reminder that nature does not care about our preference for clean categories. It cares only about whether conditions are possible, and if they are possible, something somewhere may learn to live with them. That answer is scientifically thrilling. It is also the sort of answer that makes a research vessel crew stare at a monitor a little longer than usual. And once you accept that such places are real, another part of the Red Sea becomes harder to ignore, because beneath the chemical oddities and the microbial survival stories there is a more basic force at work. These basins are not strange by accident. They are tied to heat rising from below, to hydrothermal circulation, to the restless geology of a rift that is still pulling itself apart. In other words, the impossible-looking water is only half the story. The other half is the fire under it, which is where the next part takes us. That hidden fire is what turns the deep Red Sea from unusual into genuinely unsettling, because those heavy brines do not sit on the seafloor in splendid isolation. They are tied to heat moving upward through an active rift, to hydrothermal circulation, and to a basin whose crust has been stretched and altered for millions of years. The Red Sea is one of Earth's youngest ocean basins, and a key place for studying the transition from continental rifting to ocean spreading. Recent work argues that seafloor spreading is occurring throughout the basin, and that the Red Sea behaves in many ways like an ultra-slow spreading ocean ridge, even where thick salt and sediment hide much of the structure from view. That matters because rifting does not simply pull land apart and then stop politely at the waterline. It thins the crust, allows hotter material from below to influence the system, creates faults and depressions, and opens pathways for fluids to move through rock and sediment. In the Red Sea, that process has helped produce deep axial basins where brines collect, and where hydrothermal input can change both water chemistry and the sediments below. Researchers describe the central deeps as places with unique genesis, where hydrothermal fluids feed into brine pools and minerals precipitate within a stratified water column. Even by the standards of deep marine geology, that is unusual. Most seas do not hide or forming systems inside layers of hot, hypersaline water. The best known example is Atlantis II Deep, which sounds theatrical enough already, and then proceeds to justify the name. It sits in the central rift of the Red Sea at more than 2,000 meters depth, and contains one of the most extreme hydrothermal brine systems known anywhere on the seafloor. Scientists have described it for decades as a pool of hot saline brine at the bottom of the central rift, and long-running measurements showed that the system was not static. Temperatures increased over time, which researchers interpreted as evidence that hot brine was being injected into the basin. In the 1970s, Nature reported estimates that the inflowing brine feeding Atlantis 2 deep ranged from roughly 110 to 210 degrees Celsius before mixing and cooling in the basin itself. That is not the temperature of a calm, sleepy seabed. That is the temperature of a system still very much alive beneath the sediments. Inside the deep brine itself, temperatures become high enough to sound wrong even after you have repeated them several times. Multiple studies describe Atlantis 2 deep as reaching roughly 68 to 71 degrees Celsius in its hottest lower convective layers, while nearby Discovery Deep is cooler but still far warmer than ordinary deep seawater, with hot brine around the mid-40s Celsius in some measurements. One geological study of later stratification in Atlantis, too, described a pre-existing lower convective layer of about 66 degrees Celsius and upper hot layers of about 55 degrees Celsius. For comparison, much of the normal deep ocean is only a few degrees above freezing. The Red Sea apparently looked at that global rule and decided it did not apply in this room. The phrase boiling brine needs a small technical caution because these waters are not bubbling like a kitchen pot on a stove in the way people instinctively picture boiling. Pressure at such depth changes the physical behaviour of heated fluids, and the brines are part of a layered hydrothermal system rather than an exposed kettle from hell. But the phrase still captures the main point well enough for a late-night listener. This is seawater transformed by extraordinary salt content, density, and geothermal input into something that behaves more like an isolated hot chemical reservoir than a normal marine water mass. Researchers have emphasized the strong temperature gradients, close to halite saturation salt concentrations in many pools, and the role of tectonic fracturing and brine-filled depressions in shaping these environments. The heat is not the only problem. It arrives bundled with chemistry that can make the deep brines difficult for most life and awkward for anyone hoping for a tidy explanation. Atlantis 2 deep and some of the other Red Sea brines are not only hot and hypersaline, they can also be oxygen-poor to anoxic, acidic and enriched in dissolved metals. One microbiology study described the lower convective layer of Atlantis 2 as having salinity around 4.4 molar, very low oxygen concentration, low pH around 5.3, and high temperature. Another review of Red Sea brine pools emphasised that these habitats represent the most extreme niches in the basin, in terms of salinity, temperature and metal content. So the deep brine is not merely warm salt water, it is a high-pressure, high-salinity, chemically stressed environment that seems determined to remove every ordinary comfort at once. Where does all of that come from? Part of the answer lies in ancient salt. Deep beneath the Red Sea are thick evaporate deposits left behind from older episodes in the basin's history. As tectonics and fluid flow act on those salt-rich layers, dissolution can generate dense brines that sink into topographic lows. Another part comes from hydrothermal and magmatic influence along the rift, which can add heat and alter the chemistry. A Nature communication study on Red Sea, deepwater chemistry explained that the region's plate movements led to a partly fractured seafloor and numerous brine-filled pools with strong temperature gradients. The same study distinguished between brines influenced mainly by evaporate dissolution and sediment alteration, and others tied more strongly to volcanic or magmatic alteration. In practice, that means the Red Sea floor hosts more than one recipe for making water deeply unpleasant. Atlantis 2 deep is especially famous because it couples the heat and chemistry with active mineral formation. Studies describe it as the largest known hydrothermal ore deposit on the ocean floor, and the only modern analogue of brine pool-type metal accumulation. The sediments beneath and within the brine are metalliferous, meaning they are rich in economically and geologically important metals such as zinc, copper, iron, and manganese, depending on the layer and process involved. A recent engineering geology review noted that hydrothermal fluids feed the brine pools, and that minerals precipitate within the stratified water column before settling into fine-grained sediment. So when scientists peer into Atlantis II, they are not merely studying a strange pool of hot water. They are watching a modern ore-forming system in action, which is thrilling if you're a geochemist and slightly alarming if you prefer your seafloor to act like stable furniture. The sediments themselves tell part of the story of hidden fire. Hydrothermal metalliferous sediments in the Red Sea deeps have unusual physical properties compared with ordinary marine muds. Researchers reported extreme characteristics such as very high compressibility, distinctive self-compaction behaviour, and signatures that affect acoustic surveying and sampling. That may sound like a detail only a specialist could love, but it matters because it reveals how persistent hydrothermal input and brine stratification alter the seafloor over time. Even the mud at the bottom is not behaving normally. The system leaves fingerprints in the water, in the chemistry, and in the structure of the sediments. It is one thing to discover a hot brine pool. It is another to find that the basin has been rewriting the seabed around it for ages. These hot brines are also dynamic rather than frozen in place as relics. Measurements over the years showed that Atlantis II Deep changed in temperature structure, and later work described new stratification within the hydrothermal brine system. Scientists have interpreted these shifts as evidence for changing hydrothermal activity and the continued injection or movement of hot fluids. In other words, the system is not merely an old scar left by past tectonics. It is still adjusting, still circulating, still expressing energy from below. That is one of the reasons researchers find it so compelling. A dead system is an archive. A living system is an archive that can also surprise you. This has broader implications for how the Red Sea works as an ocean basin. Because spreading is active along the basin, and because salt and sediments hide much of the ridge structure, the deep Red Sea can look deceptively quiet from the surface while remaining geodynamically busy below. A 2021 Nature Communications paper argued that ocean spreading has been underway throughout the basin for about 13 million years, and that hidden axial volcanic highs and segmentation trails are still visible in geophysical data beneath the sediment and salt cover. That means the fire under the brines is not an isolated curiosity. It belongs to the larger story of a young ocean still assembling itself, one that continues to create the conditions for heat flow, fluid movement, and deep chemical oddities. There is also something quietly unnerving about how the Red Sea keeps combining opposites. In one mental picture, a young ocean basin is opening. In another, ancient evaporate layers are dissolving. In one place, hydrothermal systems are delivering heat from below. In another, dense brines are sitting in isolated depressions like heavy liquid vaults. The whole setup feels engineered for maximum scientific fascination. It is as though plate tectonics, sedimentary history, and seawater chemistry met in a conference room, agreed to collaborate, and then neglected to warn the rest of us. The result is a basin where the ordinary division between geology and oceanography becomes difficult to maintain because the seafloor and the water column are shaping each other directly. Not all Red Sea brines are as hot as Atlantis II, but taken together they show a wide range of origins and behaviours. The basin contains numerous deeps with different geochemical signatures. Some are strongly influenced by hydrothermal input and volcanic or magmatic processes. Others owe more to evaporate dissolution, sediment interaction, or hydrocarbon-rich settings. A 2020 Nature Communications study discussing Red Sea deep water chemistry summarised this by describing two distinct brine pool types, and noting that some pools are particularly rich in methane and hydrocarbons, while others are more strongly tied to volcanic or magmatic alteration. So even within the Red Sea's strange underworld there is variety. It is not one impossible place, it is several. That does not make it more comforting. It just means there are multiple ways for the deep basin to be difficult. And because all of this happens in deep water under enormous pressure, scientists do not get to inspect it casually. They rely on coring, submersibles, remotely operated vehicles, temperature profiling, seismic data, chemical sampling, and geophysical surveys. Every data set is hard-won. Every sample has to survive collection and interpretation from an environment that is unlike most of the ocean floor. That is part of the Red Sea's hold on the scientific imagination. It is not merely extreme, it is extreme in ways that are operationally awkward. The basin does not just contain mysteries, it charges admission in equipment, logistics, and patience. The practical stakes are not small either. Researchers have long been interested in Atlantis II and related deeps for what they can teach about hydrothermal mineral deposits, basin evolution, fluid rock interaction, and the limits of habitability. There has also been obvious interest in the metalliferous sediments themselves as potential resources, which is one reason engineering studies now discuss characterization, sampling difficulties, and mining implications. Once a geological system is both scientifically unique and materially valuable, human attention tends to become very focused indeed. The Red Sea's hidden fire is therefore not just an academic curiosity. It is tied to questions about resources, environmental risk, and how much disturbance such fragile and unusual systems could tolerate. Still, what tends to linger in the mind is the image: a bright, reef-filled sea above. Far below, a rift. Inside that rift, a depression. Inside that depression, a dense lake of brine. Inside that brine, intense heat, low oxygen, acidic conditions, dissolved metals, and a sediment pile quietly recording the consequences. It is a very efficient way to ruin anyone's simple picture of what a seafloor should look like. Scientists are not terrified because the Red Sea is chaotic in a theatrical sense. They are unsettled because the heat below proves that the basin is still active, still changing, and still capable of producing conditions that feel closer to a planetary stress test than to ordinary marine life. And yet, even in that heat, life finds a foothold. That may be the strangest part of all. For every chemical barrier the deep brines put in place, some organism has worked out a way to persist, adapt, or even thrive. So once the hidden fire has done its work and the water has become hot, dense, and hostile, the story does not stop there. It becomes a story about what can live in darkness, under pressure, when almost every normal rule has been pushed aside, which is where the next stretch of this journey begins. Before anything learns to live in a place like this, the place itself has to be built, and the Red Sea is still being built now. Not in the dramatic sense of a continent suddenly snapping in half before breakfast, but in the slower, steadier way the Earth usually does these things. The crust beneath the region has been under tension for millions of years as Arabia moved away from Africa, helping form the Red Sea and the broader triple junction system that also links to the Gulf of Aden and the East African Rift. The process is slow by human standards and enormous by geological ones, which is a very efficient way for the planet to make important changes, while giving us almost nothing obvious to look at on an ordinary Tuesday. That quiet pulling began long before any modern coastline existed in its present form. One major line of evidence places the start of the Red Sea Rift system, with the Afar Plume beneath northeastern Africa at about 31 million years ago, while actual plate separation followed later, around 25 million years ago. In other words, first the region was heated, uplifted and weakened, and only after that did it begin to part in earnest. The Red Sea, then, was never just a convenient strip of water between two shores. It was the surface expression of a deeper mechanical problem, the kind that starts underground, works patiently, and eventually rearranges geography on a continental scale. For a long time, geologists argued over exactly what stage this basin had reached. Was it still mainly a continental rift, caught in the awkward middle of being stretched but not fully oceanic? Or had it already become a true spreading centre, making new oceanic crust along its length? A 2021 study pushed strongly toward the second view, arguing from earthquake data, vertical gravity gradient data, and bathymetry that the Red Sea is a mature ocean basin, in which continuous seafloor spreading began along its entire length around 13 million years ago. That conclusion matters because it changes the mood of the whole place. A rift sounds like something becoming unstable. A spreading centre sounds like something with no intention of stopping. Part of the confusion comes from the fact that the Red Sea hides its structure unusually well. Thick salt layers and younger sediments cover large parts of the basin, especially in the central and northern sections, making it harder to see the ridge system beneath in the tidy way geologists would prefer. The underlying tectonic story is still there, but much of it is draped over, softened, or buried under deposits that make the basin look quieter than it really is. This is one of the Red Sea's favourite habits. It lets the calm surface and the buried geology collaborate in giving the impression that everything is more settled than it actually is. Then a better data set arrives and the seafloor turns out to be keeping far fewer secrets than the sediment cover suggested. The movement itself is not especially fast, which only adds to the sense of quiet. One study of Red Sea hydrothermal activity describes the rift as ultra-slow spreading, with rates ranging from under 10 to over 16 millimeters per year depending on location. That is not the sort of speed likely to ruin anyone's beach day in real time, but it is more than enough given enough years to create new crust, reshape basin geometry, maintain fault systems, and keep magma and hydrothermal fluids involved in the story. The Earth does not need to hurry when it has millions of years available and an entire lithosphere to work on. The southern part of the system gives the game away a little more clearly. Volcanic islands and submarine volcanism there offer direct proof that this is not merely an old wound filling with seawater. In the southern Red Sea, eruptions at Jebel at Tair in 2007 to 2008 and in the Zubair archipelago in 2011 to 2013 produce spectacular reminders that magmatism is still active. A nature communication study on the birth of two new volcanic islands concluded that the southern Red Sea ridge had been magmatically active for at least 2 decades, supporting the presence of an active spreading centre. It is one thing for geologists to infer movement from gravity data and magnetic structure. It is another for the sea to respond by making fresh islands and gently informing your atlas that it may already be outdated. Those eruptions are dramatic enough to attract headlines, but the more persistent sign of ongoing activity lies underwater, where faults, magma, and circulating fluids continue their work out of sight. The recent discovery of widespread diffuse hydrothermal venting at Atiba Mons, the largest axial volcano in the Red Sea, added direct observational proof to what had long been inferred from hot brines and metalliferous sediments. The vent fields there are associated with recent magmatic activity, and observations of fresh basaltic glasses and lava flows suggest eruptions younger than about 1,000 years. That may sound comfortingly old to a human listener trying to sleep, but in geological terms it is very recent. More like a warm appliance left running than a fireplace long gone cold. Once you understand that, the Red Sea starts to feel less like a sea in the usual sense, and more like a narrow young ocean stretched between two still argumentative margins. Western Saudi Arabia preserves a related record of long-lived volcanism in the form of vast Harat lava fields, emplaced over roughly the last 30 million years. A recent USGS report notes that these volcanic fields are broadly associated with the 3 rift valleys radiating from the Afar region, and that the Afar plume helped thermally weaken the region, enabling Arabia to separate from Africa along the Red Sea and Gulf of Aden. So the splitting is not confined neatly to a single line in the water. The wider region carries the marks of heat, thinning, uplift, and magma over a very large area. The northern end of the system complicates the picture even further, because the Red Sea does not simply continue northward in one clean tectonic style. At the Gulf of Aqaba and Dead Sea Fault system, the plate boundary shifts into a transformed setting, linking the northern Red Sea to structures farther north. According to scientific reports, this transformed boundary originated in the Miocene and effectively ended continental rifting in the Gulf of Suez, with initiation around 14 to 11 million years ago. That means the northern gateway of the Red Sea is not just an ocean-opening story, it is also a story of sideways motion, strike-slip faulting, and seismic hazard. Even at the point where one might hope the geometry would simplify, the Earth remains committed to keeping the assignment slightly more difficult than expected. That transform connection matters because it keeps the region seismically alive. The Gulf of Aqaba has produced damaging earthquakes, including a major offshore event in 1995 that caused casualties and building damage over a broad area. Scientists studying the area note that seismicity remains concentrated in key subbasins, and that future hazard assessment is increasingly important as development grows around the Gulf. So when we say the Earth is quietly pulling itself apart here, quietly only works in a relative sense. The movement is gradual, but the strain is real, and every so often the crust reminds nearby cities and coastlines that slow tectonics can still deliver very sudden results. There is also a broader reason scientists keep staring at the Red Sea with such intensity. It offers a rare chance to watch several stages of plate boundary evolution living side by side. There is plume influence in the south and southwest. There is spreading beneath a semi-enclosed sea. There are salt-covered segments masking the ridge. There are transform motions to the north. There are volcanic islands at the surface, hydrothermal vents along the axis, hot brines in deep basins, and rift flank uplift recorded on land. Usually textbooks spread these ingredients across several different places. The Red Sea gathers them into one long narrow basin and asks everyone to keep up. That makes it invaluable as a natural laboratory and slightly exhausting as a place to summarize in one neat sentence. The semi-enclosed nature of the basin adds another layer to the tension. Because the Red Sea is connected to the wider Indian Ocean only through the narrow and shallow Bab el-Mandeb Gateway, its bottom waters are warmer and saltier than those of most other oceans. A recent study on Hatiba Mons noted bottom water salinity around 40 parts per thousand, compared with a global average around 35 parts per thousand, and bottom water temperatures about 18 degrees Celsius, warmer than those in most deep oceans. That means the tectonic system is not operating beneath ordinary ocean water, it is operating beneath water that is already chemically and thermally unusual. The seafloor is opening under a marine basin that has its own environmental oddities, which is probably why the Red Sea so often feels less like one process and more like several difficult processes sharing office space. This is why the phrase young ocean is both accurate and somehow not quite enough. A young ocean sounds almost charming, as though the Red Sea were simply in its early development and would soon settle into something more familiar. But young oceans are not gentle in any meaningful geological sense. They involve stretching crust, thinning lithosphere, magmatism, hydrothermal circulation, faulting, uplift, subsidence, and the gradual creation of entirely new seafloor. The Red Sea is doing all of this while bordered by populated coasts, major shipping routes, and ecosystems that already live near environmental limits. Scientists are not unsettled because the Earth is behaving unusually here. They are unsettled because it is behaving exactly as plate tectonics predicts, only in a place where every consequence feels close to the surface. And yet, for all the force involved, the basin remains deceptively calm when viewed from above. Sunlight falls on reefs, ferries and cargo ships pass through, divers descend over coral walls. From that perspective, it is easy to forget that the crust below is still under extension, that magma has not left the conversation, and that a sea can be both beautiful and mechanically unfinished at the same time. The Red Sea has become one of the clearest reminders that a place does not need to look violent in order to be active. Sometimes the most unsettling landscapes are the ones that carry on looking perfectly composed, while deep below them the ground is still opening, the fluids are still moving, and the next surprise is already being prepared in the dark, which is exactly the sort of setting where unusual life begins to make itself at home. And once the crust has opened enough, once the heat has found its paths upward, and the brines have settled into those heavy, hostile basins, the next question becomes almost impossible to resist. What exactly manages to live down there? Because if the deep Red Sea were only a geological curiosity, it would already be extraordinary. But it is not only hot, salty, acidic and oxygen-starved in places. It is inhabited. The same basin that seems designed to repel life has become one of the clearest demonstrations that life is less fragile, more inventive, and occasionally far more stubborn than our ordinary expectations allow. In the Red Sea's deepest, harshest environments, especially its brine pools and hydrothermal sites, scientists have found dense microbial communities, specialized metabolic systems, and even pockets of larger animals exploiting the edge of danger rather than retreating from it. That is what makes this part of the Red Sea so unsettling. It is not merely that the conditions are extreme, it is that the usual logic of too harsh for life keeps failing. Reviews of Red Sea brine pools describe them as the most extreme habitats in the basin in terms of salinity, temperature, and metal content, and yet they host rich bacterial and archaeal communities. These organisms are not there by accident, and they are not merely lingering at the margins. They are adapted to hypersalinity, low oxygen or complete anoxia, unusual chemistry, and in some cases elevated temperature. The result is a living system built out of metabolisms that would seem improbable if we had not repeatedly sampled them, sequenced them, cultured some of them, and watched them keep proving the point. A good place to begin is the brine-seawater interface, because that thin transition zone is often where the deepest strangeness becomes biologically useful. In Cabrit Deep, one of the best-studied Red Sea brine pools, researchers measured a remarkably sharp shift across only a few meters. Salinity jumps from roughly 4 to 26% sodium chloride. Temperature rises from about 21.6 to 23.4 degrees Celsius. Methane increases dramatically. Hydrogen sulfide appears. The pH drops from about 8.1 to 5.5, and oxygen falls to 0. That is not a gentle environmental gradient. That is a biochemical cliff. And yet the interface acts as a particle trap, concentrating organic material and creating a niche where specialized microbes can feed, recycle matter, and exploit chemical differences that most larger organisms would experience as a rather strong suggestion to leave immediately. Scientists studying Cabrit Deep found exactly the sort of organisms one might hope for if one were trying to test the outer limits of microbial tolerance. Novel halophiles were isolated there under strictly anaerobic conditions, including members of the genus Halanaerobium, which were the first deep-sea anaerobic brine pool representatives of that group obtained at the time. The same work concluded that novel halophils thrive in the anaerobic Cabrit system and may contribute significantly to the breakdown of organic matter accumulated at the brine-seawater interface. That matters because it shows that the edge of the brine is not a dead boundary. It is an active biochemical workshop. Organic material falls in, chemistry becomes severe, and microbial communities get to work doing the quiet metabolic labour that holds the whole extreme ecosystem together. The deeper researchers have looked into Red Sea brine systems, the more they have found that the life there is structured by layers, almost as if the sea itself has been sorted into floors of a very strange building. In the water column overlying Atlantis 2 Deep and Discovery Deep, 16 srDNA sequencing showed strong vertical stratification in microbial communities from the surface to 1,500 meters. Near the surface, bacteria were dominated by cyanobacteria. Deeper down, proteobacteria became more abundant. Among archaea, upper waters were rich in Euarchaeota, such as Halobacteriales, while deeper layers shifted toward Crenarchaeota, including Desulphura coccales. The researchers concluded that the microbial communities differed from those known in many other marine water columns, and that the depth-wise changes reflected adaptation to the Red Sea's particular environments. Even before one reaches the brine itself, life in the deep Red Sea is already reorganizing around the basin's unusual conditions. That layered quality is one reason the Red Sea feels so unlike a normal sea. Every change in depth can bring a change in chemistry, and every change in chemistry can favour a different set of organisms. Outside a brine pool, aerobic microbes may dominate. Closer to the interface, anaerobic metabolisms begin to take over. Inside the brine and in the sediments below, sulfate reducers, methanogens, fermenters, and other anaerobes become central players. The neon brine pools in the Gulf of Aqaba showed exactly this pattern. In outer sediments, microbial communities were dominated by lineages associated with aerobic metabolism. Moving inward toward the brine margin, anaerobic groups increased. In the pool sediments themselves, a diverse suite of anaerobes dominated, including organisms associated with sulfate reduction, methanogenesis, reductive dechlorination, and fermentation. The message is consistent. Life is not absent in these harsh places. It is reorganized around the conditions rather than defeated by them. That reorganization becomes even more impressive when one remembers just how severe the Red Sea's extreme zones really are. The brine pools are described in current literature as among the most extreme habitable environments on Earth. They're relatively rare worldwide, yet the Red Sea hosts an unusually large number of them. Their importance is not only biological, but biological significance is one of the reasons they keep drawing so much attention. They offer a setting where salinity, anoxia, low pH, elevated temperature, and unusual dissolved chemistry come together all at once. In an ordinary marine ecosystem, a single one of those pressures can be difficult. Here, multiple pressures are stacked into the same habitat. Any organism thriving there is already telling scientists something important about the flexibility of life. This is where microbiology and a kind of calm scientific disbelief begin to overlap. Researchers are not simply finding microbes in the Red Sea. They're finding microbes whose enzymes and metabolic pathways function under conditions many industrial processes would consider unpleasant, and many cells would consider catastrophic. Reviews of Red Sea brine pools emphasize the promise of these communities as sources of extremozymes, enzymes adapted to harsh biophysical conditions. That has made the basin valuable for biotechnology as well as basic science. The same physiological tricks that let a microorganism survive hot, salty, low oxygen, metal-rich water may produce enzymes useful for industrial reactions, biocatalysis, and other applications. There is something wonderfully practical about the whole arrangement. Nature invents a survival strategy at the bottom of a chemically hostile sea, and humanity immediately starts wondering whether it might help run a factory more efficiently. Some of the most intriguing Red Sea findings point beyond industry and toward deep history. Because these brine systems combine salinity, warmth, metal-rich chemistry, and low oxygen, scientists often treat them as analog environments for early Earth, and as clues for what kinds of life might be possible in extraterrestrial settings with liquid water and severe chemical gradients. The Red Sea's deep environment is not a direct copy of the early planet, of course, but the comparison is scientifically useful. The bottom waters are warmer and saltier than much of the global deep ocean, and the chemical extremes of some brine pools push life into modes of survival that may echo conditions more common on the young Earth. When microbiologists study a Red Sea extremophile, they are often asking two questions at once. How does this organism survive here? And what does that tell us about what life can become when the world around it is hostile by default? Still, microbes are only part of the story, and this is where the Red Sea becomes especially eerie, because the edges of these deadly environments do not remain empty. Larger animals gather there. They do not inhabit the harshest brine itself in the way microbes can, but they exploit the interface in ways that feel almost unsettlingly efficient. The neon brine pools provided one of the clearest examples. Researchers reported a rich metazoan assemblage around the pools, including eels, a big-eye hound shark, flatfish, shrimp, and mollusks. These animals did not appear there randomly. Observations were consistent with predators deliberately using the brine as a feeding opportunity, cruising the surface and taking advantage of organisms stunned or killed by the anoxic hypersaline waters. It is a startling picture. The pool itself acts like a trap, and nearby animals behave as though they know exactly how to use it. The details are almost too neat. In the Neom system, the eel was observed repeatedly dipping into the brine, apparently retrieving prey that had been shocked or killed by the pool. Shrimp of the genus Plesionica amassed on topographic highs around the rim and were seen venturing far out over the brine surface to pluck out disabled organisms. The description in the paper is very restrained, as scientific descriptions generally are, but the scene it evokes is wonderfully strange. Imagine a deep-sea landscape where a hidden chemical boundary functions a little like an invisible snare, and local predators have incorporated that hazard into their routine. The Red Sea, even when it is being ecological rather than geological, remains committed to making everything slightly more unsettling than expected. Along the rim itself, an even stranger resident appears. A black-coloured bivalve, Apache Corbula muriatica, occupies a narrow band just above the brine seawater interface. In the Neom pools, the species was reported in a zone only about 20 centimetres thick above the brine surface, and the same narrow band distribution has been documented around the rim of the Valdivia deep brine pool in the central Red Sea. That narrowness matters. It suggests these bivalves are not merely tolerant of unusual conditions, they appear to be tied to them, living in a slice of habitat defined by elevated salinity, low oxygen, lower pH, and modestly warmer water, exactly where brine and ambient seawater mix. A clam choosing to live in a chemically stressful strip of water that most animals avoid is not the sort of thing one expects to explain calmly to a sleepy listener, and yet here we are. The likely reason is food. The Neom study suggested that the bivalves and other associated animals may be sustained directly or indirectly by chemosynthetic microbial activity around the pool margins and in the waters above them. That is a recurring pattern in extreme marine systems. Microbes exploit chemical gradients, turning dissolved compounds into biomass, or making energy available through pathways ordinary surface ecosystems do not rely on as strongly. Larger organisms then feed on the microbes, on detritus, or on one another. In other words, the Red Sea's harshest depths are not barren. They are productive in a very different way. Their food webs are built around chemistry as much as sunlight, and the edges of toxicity become the edges of opportunity. The hydrothermal fields of Hatiba Mons add another version of this story. There, active low-temperature venting has created extensive iron-rich mounds coated with abundant microbial mats. These mats occur in several distinct forms, from fluffy white or orange heaps to fur-like coverings around diffuse flow and microbial films associated with chimneys and bowl-like vent structures. Sequencing work from Hatiba Mons found a remarkably broad prokaryotic diversity, including 72 phyla overall in the original 2023 survey, with bacteria dominating and important archaeal groups also present. A later genome-resolved study described the site as an iron-rich hydrothermal system whose communities include Bathyarchaea, Chloroflexi, and various members of Pseudomonodota involved in carbon, nitrogen, sulfur, and especially ion cycling. That last point is important. These vents seem to run less on the classic drama of sulfide and more on iron-driven metabolisms, which gives the Red Sea yet another way to be odd. Hatiba Mons is particularly interesting because, despite hosting abundant microbial communities, it appears to lack the kind of specialised chemosymbiotic vent fauna seen at many other hydrothermal systems. The 2023 vent field study reported common deep benthic organisms near the mounds but no specialised deep vent fauna. The authors suggested several possible reasons, including the low-temperature iron-rich character of the fluids, the absence of the sort of sulfide oxidising bacteria often associated with symbiont hosting vent animals, the warm and highly saline deep Red Sea seawater, and the basin's geographic isolation. In other words, the vents are alive, but not in the exact castless manner a vent biologist might expect from other ocean ridges. Even here, where one might think hydrothermal systems would follow a familiar script, the Red Sea insists on improvising. That absence is revealing in its own way. It suggests the Red Sea does not merely host extreme life, it filters it. The deep basin is warm and salty even before hydrothermal fluids arrive. It is relatively isolated from the broader global ridge system by the narrow and shallow connection through the Bab el-Mandeb, and the 2023 Hatiba Mons paper notes that this limited connectivity may hinder colonization by deep-sea species from the Indian Ocean. The Red Sea also experienced a major extinction event around the last glacial maximum, after which its ecosystems were effectively rebuilt. That combination of isolation, unusual baseline conditions, and interrupted history may explain why some lineages flourish, while others never quite establish themselves. A place can be habitable and still remain highly selective. There is something quietly humbling about that. Human beings often talk about extreme environments, as if extremity were a universal category, one harsh place much like another. The Red Sea keeps showing that extremes come with their own details and local rules. A vent field in the Atlantic is not the same as a vent field in a young semi-enclosed warm salty basin. A brine pool in the Gulf of Mexico is not identical to a Red Sea brine pool shaped by different tectonics, chemistry, and water mass history. Life responds not only to harshness in general, but to particular combinations of pressure, salinity, heat, oxygen, and fluid chemistry. That is why Red Sea organisms matter so much scientifically. They are not generic survivors, they are specialists, built by a place that keeps layering difficulty on top of difficulty and then rewarding very specific solutions. And because these are specialists, they often carry with them clues to processes we still do not fully understand. The methane-rich and sulfide-bearing gradients in places like Kibrit Deep point to microbial transformations of carbon and sulfur. The iron-rich microbial mats of Hatiba Mons point to life organized around metal cycling in ways still being mapped through metagenomics and microscopy. The neon pools reveal how metazoan assemblages can cluster around microbial production, even where the central habitat itself is lethally anoxic. Every one of these systems adds another piece to the broader puzzle of how life structures itself under stress. The Red Sea, then, is not terrifying only because it is harsh. It is terrifying because its harshness keeps turning into biology. Even the visual impression matters. Scientists descending with remotely operated vehicles do not simply encounter abstract data. They see boundaries in the water, microbial staining around the pool rim, black bivalves arranged in a thin belt, shrimp hovering above an invisible hazard, and vast hydrothermal mounds covered in white, yellow, or orange microbial mats. They see a place where deadliness and productivity occupy adjacent centimetres. It is one thing to read that a brine pool is anoxic and hypersaline. It is another to watch an animal approach the interface, recover prey from it, and then drift back into ordinary seawater. The Red Sea turns ecological theory into scenes that feel almost too deliberate, as though the environment itself has staged a demonstration of how closely life can live to catastrophe without being absorbed by it. That, perhaps, is the real discomfort at the centre of this part of the story. We tend to imagine survival as a retreat from danger. The Red Sea's harshest depths often show the opposite. Microbes lean into the chemistry. Bivalves occupy a narrow strip at the interface. Shrimp patrol the margin. Predatory fish use the pool's deadliness as a hunting aid. Even where specialised vent fauna seem limited, microbial life expands across iron-rich mounds in abundance. The pattern is not avoidance, it is exploitation. Life does not merely endure the Red Sea's extremes, quite often it uses them. That makes the basin scientifically thrilling and faintly unnerving, because it means the line between impossible and inhabited is much thinner than most of us would like to believe. And the closer scientists look, the less final any explanation feels. New brine systems continue to be discovered. New genomic work continues to reveal uncultured lineages and previously unrecognised metabolic roles. The big picture is clear enough now to be astonishing, but the details are still coming in. Which microbes dominate under which chemical conditions? How stable those communities remain over time? How much exchange occurs between brine interfaces, vent systems, and the surrounding deep basin? How resilient these organisms are to disturbance? These are not trivial questions, especially in a sea that is increasingly important as a natural laboratory for warming oceans and environmental stress. A place this selective, this unusual, and this biologically inventive can teach a great deal, but it can also be damaged before we fully understand what it has been teaching. So beneath the surface, in the darkest and harshest depths of the Red Sea, the story is not of emptiness. It is of a living edge. It is of microbes turning chemistry into survival, of animals gathering where normal seawater gives way to something dangerous, and of an ecosystem that feels stitched together from conditions no sensible planner would ever choose. And yet it works. It works because the Earth does not build environments for comfort. It builds them according to physics and chemistry, and then life arrives and starts improvising. In the Red Sea, that improvisation has produced one of the strangest deep communities on the planet, which is remarkable enough on its own. But once you see how closely that life depends on boundary layers, dense brines, and isolated basins, another possibility begins to creep in. These depths do not merely host life, they also trap things, preserve things, and keep things where they fall, which is where the next part of this journey moves. That thin line between survival and catastrophe also explains why the deep Red Sea behaves less like an ordinary seafloor and more like a trap that has had millions of years to refine its technique. In most parts of the ocean, whatever sinks to the bottom is still subject to currents, scavengers, burrowing animals, chemical breakdown, and the general untidiness of a living seabed. Things fall, yes, but they rarely stay in a neat and readable way. The deep Red Sea, especially where brine pools occupy depressions on the floor, changes that pattern. These pools are stable accumulations of hypersaline fluid sitting in seabed lows, and because they are denser than the surrounding seawater, they form sharply defined interfaces and remain pooled rather than mixing away. That alone makes them unusual. What makes them truly unsettling is what that stability allows them to keep. The first part of the trap is simple physics. Dense water sinks. Very dense water settles and stays put if the basin geometry allows it. The neon brine pools in the Gulf of Aqaba, for example, were found at 1,770 metres depth in the Aragonese Deep, where one main pool stretches about 260 metres long and 70 metres wide, covering roughly 10,000 square metres, with brine up to 6 metres thick in its centre. That is not a passing plume or a temporary stain in the water. It is a heavy body of fluid lying in a depression, with a visible and abrupt density boundary between the pool and the surrounding seawater. Researchers even used dye to show how stark that boundary is. Once you have a basin like that, you have the physical foundation for a very effective collector. Things drifting, settling, or sliding downslope do not simply land on a normal seabed. They enter a dense, still chemically hostile reservoir that is remarkably good at holding on to them. The second part of the trap is the interface itself. A brine seawater boundary in the Red Sea is not only a dividing line between one kind of water and another. It is a zone where density, chemistry, oxygen, and often pH change abruptly, and those steep gradients help create what researchers have described as an in situ particle trap for organic and inorganic material. At Kibrit Deep, the interface was shown to host organic matter enrichment, and microbial studies concluded that novel halophiles there likely contribute to anaerobic degradation of that material after it accumulates at the boundary. The review literature makes the point even more clearly. The density gradient at the brine seawater interface traps particles and increases nutrient availability, which in turn supports dense microbial growth. So the trap is not passive. It does not merely hold whatever arrives. It concentrates material at exactly the zone where specialized microbial communities can begin taking it apart, transforming it, and incorporating it into a different kind of ecosystem. Then comes the part that makes sedimentologists especially happy and almost everyone else slightly uneasy. In the Neum brine pools, researchers found that anoxia entirely excludes bioturbating megafauna. That means the larger bottom-dwelling animals that would normally churn, mix, disturb or blur the sediment record are effectively absent inside the pool. Away from brine pools in the Gulf of Aqaba, cores are heavily bioturbated. Inside the brine environment, that churning is gone. The layered deposits remain much more pristine. In practical terms, the trap does not just catch material, it keeps later visitors from rearranging it. Imagine dropping pages into a drawer that then locks itself and sends away anyone likely to shuffle the papers. That is roughly what an anoxic brine pool does to the seafloor record. The brine also shields the bed from currents. That detail matters more than it might seem. In the open deep sea, bottom currents can winnow away fine material, erode surfaces, and disturb delicate layering over time. The Neum study states that the high density of the brine effectively shields the bed from deep water currents that would otherwise winnow or erode the bathyal seabed. So now the trap has acquired another useful feature. Not only does it keep out burrowing animals, it also suppresses the hydrodynamic fussiness that would normally edit the archive. The result is a setting that preserves sequences with a level of detail hard to achieve elsewhere nearby. It is one of the rare cases in marine science where the environment is both hostile and helpful, depending entirely on whether you are a worm or a paleoclimate researcher. That preservational quality is not theoretical. In the main Neum pool, the preserved stratigraphy spans at least 1,200 years and includes a combination of turbidites, likely related to flash floods and local seismicity, along with terrestrial sediment interpreted as tsunamigenic in origin. The authors argue that the pools have unique potential to archive historical tsunamis, flash floods, and seismicity in the Gulf of Aqaba on millennial timescales. This is where the trap becomes more than a local curiosity. It starts functioning as a recorder of hazard history. Earthquakes shake slopes, floods send pulses of sediment seaward, tsunamis disturb coastal systems, and the pool quietly receives and keeps the evidence. A normal seabed might smear those signals. The brine basin preserves them with unusual fidelity. In a sense, the deep Red Sea does not only keep what falls into it, it keeps the memory of why it fell. That memory extends beyond the Neum discovery. Studies of other Red Sea brine systems and related pools elsewhere have long recognised the preservational benefits of anoxia, low bioturbation, and stable density stratification. The Red Sea review literature treats these pools as exceptional habitats not only for extremophiles, but also for the environmental records held in their sediments. The 2024 work on pore waters from the Neum complex likewise emphasises brine pools as unique windows into geological and planetary processes, sedimentary records, and extremophil habitats. Once again, the key point is not merely that the pools are odd, it is that their oddness has consequences. Chemistry alters ecology, and altered ecology changes preservation. In the Red Sea, harshness becomes archival quality. There is another dimension to the trap, and this one is biological rather than sedimentary. The brine pools are dangerous to metazoans. Waters just above Atlantis 2 Deep have been reported as depleted of macrofauna, while at Kebrit Deep the pelagic fauna is enriched at the interface rather than inside the brine. The Oxford study from 2016 describes the deep-sea anoxic brines of the Red Sea as too harsh for metazoans, while noting that the brine seawater interface harbours dense microbial populations and that fauna appeared enriched at the Kebrit interface. That means the pool itself can act as a lethal zone, but the edge of that danger becomes biologically attractive. It is the marine equivalent of everyone gathering around a machine that is clearly dangerous, because annoyingly, that is also where the interesting food keeps appearing. The Neum pools make this much easier to picture. There, researchers observed a rich metazoan assemblage around the pools, including eels, a big-eye hound shark, flatfish, shrimp and mollusks. Their interpretation was that predators exploit organisms incapacitated or killed by the harsh brine. The eel was seen dipping into the brine and retrieving prey. Shrimp ventured out over the brine surface to pluck stunned organisms. This is what makes the phrase "perfect trap" feel entirely justified. The pool does not just capture sediment and preserve hazard records. It can also disable animals that move too close, creating a feeding opportunity for species that have learned where the boundary lies and how to use it without crossing too far. Nature can be very elegant. It can also be very direct when arranging dinner. Even organisms that do not hunt there can treat the interface as a narrow opportunity zone. The black bivalve Apache corbula muriatica occupies a very thin band just above the brine seawater interface in the Neom pools, much as it does around the Valdivia Deep in the central Red Sea. This narrow distribution strongly suggests that the animal is tied to the unusual conditions at the rim rather than merely tolerating them. The likely explanation is access to microbial productivity or detrital resources associated with the interface. In other words, the trap does not simply destroy and preserve, it also creates edges where life can crowd into a tiny slice of habitable space. If most of the pool is hostile and most of the surrounding seabed is comparatively poor in opportunities, then the boundary becomes prime real estate in the strangest possible neighbourhood. What makes these traps especially effective is how many processes they combine. There is topography because the pools sit in depressions. There is density because the brine is so much heavier than surrounding seawater. There is chemistry because anoxia, low pH, salinity, and in some cases elevated temperature make the environment difficult for ordinary benthic life. There is microbial response because those gradients promote dense and specialized communities. There is ecological opportunism because predators and boundary-dwelling organisms use the edge without entering the most lethal part. And there is preservation because the absence of burrowers and the shielding from currents prevent later disturbance. In a simpler sea, you might get one or two of these. In the deep Red Sea, you get all of them layered together, which is precisely why scientists find it so valuable and so unsettling. There is also a broader geological reason the Red Sea keeps building these kinds of traps. The region has numerous brine pools because the basin contains the right combination of structural lows, evaporate dissolution, and tectonic setting. The 2022 Neom paper notes that even across the Red Sea, Mediterranean, and Gulf of Mexico, deep-sea brine pools are relatively rare, with only a few tens known globally, and yet the Red Sea holds the highest number among these venues. Many of the axial pools are tied to the rift-spreading axis and are warmer than ambient Red Sea seawater, while Neom extends the phenomenon into the Gulf of Aqaba in a different depositional setting. This means the trap mechanism is not a one-off curiosity. It is part of a regional habit. The Red Sea keeps producing the kinds of depressions and dense fluids that let it hold on to things unusually well. The phrase "keeps what falls into it" also applies to chemical signals and organic matter. At Kebret Deep, organic matter is enriched at the interface, and the local microbial community appears built around taking advantage of that enrichment. The review literature emphasizes that the density gradient traps both organic and inorganic particles, effectively increasing nutrient supply and the potential for bacterial growth. So the interface is not just a place where matter pauses before sinking farther. In many cases it is where matter accumulates, is metabolized, and becomes the basis for localized food webs and biogeochemical cycling. This is important because it means the trap alters the fate of what it catches. A particle entering such a system does not simply sink and vanish. It may be held, consumed, chemically transformed, preserved in sediment, or all of those in sequence. There is something almost administrative about how efficient the whole arrangement is. Most deep-sea environments lose clarity over time because so many agents keep reworking the material. In a Red Sea brine pool, many of those agents are suppressed or redirected. Burrowing megafauna are excluded by anoxia. Currents are damped by the dense brine. Organic inputs are concentrated at the interface. Specialized microbes process what arrives. Predators gather where the pool disables prey. Sedimentary layers remain legible. It is not just a trap in the sense of holding things, it is a sorting system. It catches, kills, feeds, archives and preserves, depending on exactly where something enters and what it is made of. A geologist sees an archive, a microbiologist sees a reactive boundary, a fish sees lunch. The pool, apparently, sees no reason these functions should be separated. That is why these environments have become so important for reconstructing regional history. A normal coastal margin can receive valuable event deposits, but those deposits are often blurred by later mixing. The Neom pools are different because they lie only about 2 kilometers from shore, close enough to receive coastal sediment from slope processes, while still preserving it unusually well. The authors specifically highlight their location at the toe of slope and their potential to archive historical tsunamis, flash floods, and earthquakes in the Gulf of Aqaba. The scientific appeal is obvious. Coastal regions are exposed to hazards, but the records of those hazards are often patchy. Here, the sea has accidentally built a deep storage locker right where some of the most useful evidence can arrive. It is a remarkably efficient arrangement if your job is reconstructing the past, and a mildly troubling one if you prefer your dangerous natural systems not to come with built-in memory. There is also an eerie contrast between the surrounding deep seafloor and the pools themselves. The Neom study describes the wider bathyal depths of the Gulf of Aqaba as a desolate mud-draped seabed with low species diversity, which is fairly typical for such depths. The pools stand in stark contrast to that monotony. The boundary between normal marine waters and the anoxic brine creates a niche where rich microbial communities develop, and these in turn support associated metazoan assemblages. This means the trap does not simply interrupt the deep sea floor, it punctuates it. Imagine a long quiet hallway, and then, without warning, a room where all the rules change, where chemistry becomes severe, where animals gather for reasons that are partly opportunistic and partly deadly, and where the floor keeps a cleaner record than the corridor outside. That is more or less what a Red Sea brine pool is doing at depth. For scientists, this is both a gift and a warning. It is a gift because such pools preserve information that might otherwise be lost, and because they provide a controlled natural setting for studying the interaction of density stratification, microbial ecology, sedimentology, and hazard history. It is a warning because environments this distinctive are also fragile. The same conditions that make them useful can be disrupted. The 2022 Neom paper explicitly argues that this bathyal ecosystem deserves protection comparable to the shallow water reefs far above it, especially given the rapid urbanization of the Gulf of Aqaba coastline. That is a sober point. The deep trap keeps what falls into it, but it cannot necessarily keep functioning the same way if the wider basin is altered around it. Archives can be damaged, boundary ecosystems can be disturbed. A place that looks indestructible because it is so harsh may still be vulnerable in very ordinary human ways, and perhaps that is what makes the trap feel so unnerving in the end. It is not merely a dramatic oddity in a remote abyss, it is a working part of the Red Sea system. It records tectonic unrest, it captures flood signals, it concentrates organic matter, it disables prey, it shelters specialized life along its rim. It keeps a cleaner memory than the surrounding seabed. It sits there in darkness doing all of this without any need for our attention, which is generally how the most impressive natural systems prefer to operate. The deep Red Sea does not announce that it is collecting evidence, it simply goes on collecting it. And once you know that, it becomes much harder to look at this sea as just a narrow strip of water between two lands. It starts to look more like a machine for preserving consequences, which is a useful thought to carry forward, because once a place can preserve that much, scientists naturally begin asking what else it has been keeping all this time. And that is where the Red Sea becomes especially unnerving for modern science, because once researchers realised the deep could trap and preserve so much, they also realised they were not just studying a strange sea. They were reading a long record written by a sea that remembers. In place after place, the Red Sea keeps offering scientists two things at once. It offers ancient evidence, sometimes thousands or even tens of thousands of years old, and then right beside that evidence it offers a very current warning about heat, stress, vulnerability, and the limits of resilience. That combination is what gives this part of the story its uneasy mood. The Red Sea is not only extreme now, it also carries a history of earlier extremes, and scientists keep finding signs that the past and present are far more closely linked here than anyone would prefer. One of the most striking recent findings concerns a question that had been hanging over Red Sea science for years. During the last glacial period, sea level fell dramatically, narrowing the connection between the Red Sea and the Indian Ocean at Bab el-Mandeb. Many researchers had assumed this would have pushed the basin into such severe salinity stress and ecological collapse that much of its marine life, especially in deep water, might have been wiped out and forced to recolonize later. But a 2025 study of deep water corals from 26 northern Red Sea sites challenged that picture. Uranium-thorium dating and geochemical analysis showed that these corals were present during and after the last glacial sea level low stand, and the study concluded that the basin did not undergo the complete ecological sterilization once widely imagined. In simple terms, the Red Sea did not die and restart in the neat, catastrophic way some models suggested. It endured. That is scientifically important. It is also slightly unsettling, because endurance here seems to mean surviving conditions that already sound close to the edge of habitability. That same study matters for another reason. Earlier work had pointed to extremely high glacial salinities, oxygen stress, and the so-called planktonic interval as evidence for basin-wide collapse. The newer deep water coral evidence says the story was more complicated. Some pelagic organisms likely vanished locally, but other groups persisted, and the chemistry and temperatures inferred from the corals suggest tolerable conditions remained, at least in important parts of the basin. The implication is not that the Red Sea was ever comfortable, quite the opposite. It is that life there may be far more resilient and patchily distributed under stress than previous broad-brush collapse scenarios allowed. Scientists do not find that comforting so much as instructive. A sea that can remain alive under such pressure may preserve resilience in one era and still be vulnerable in another, and those are not always easy states to tell apart while events are unfolding. The modern discoveries in the deep have been just as striking. In 2022, scientists reported that neon brine pools in the Gulf of Aqaba, the first brine pool complex discovered outside the Red Sea proper, at about 1,770 metres depth in the Aragonese Deep. The main pool alone covers about 10,000 square metres, and the broader complex preserves at least 1,200 years of stratigraphy. That record includes turbidites likely linked to flash floods and local seismicity, along with terrestrial sediments interpreted as tsunami-genic in origin. This is an extraordinary combination. A sea already known for extreme chemistry and deep brine basins suddenly revealed another such basin in a tectonically active pull-apart setting close to shore, one that appears uniquely positioned to archive coastal hazards over long timescales. The practical consequence is hard to miss. Scientists are not only finding strange habitats, they are finding highly effective natural recorders of earthquakes, floods, and tsunami-linked sedimentation along a coastline that is developing rapidly in the present. A 2024 study pushed that archival role further by showing that sediment-poor waters beneath the Gulf of Aqaba brine pools also retain signals of climate and tectonic disturbance. The authors concluded that these pore waters record transient and dynamic changes in the deep depositional environment and reflect the interplay among climate, tectonics, and sedimentation along a rapidly urbanizing coastline. That phrase, rapidly urbanizing coastline, is doing a lot of work. It means the archive is not only ancient, it sits next to modern human expansion. The Red Sea, in other words, is preserving evidence of past unrest, while people continue building around it in the present. Scientists keep finding new layers of memory there, and every new layer seems to come with a quiet reminder that the region is not finished producing the kinds of events it records. Then there was the hydrothermal surprise. For decades, researchers had indirect evidence that the Red Sea Rift hosted hydrothermal activity. Metalliferous sediments, hot brines, and chemical anomalies all pointed in that direction. But until very recently, there had been no direct visual confirmation of active vent fields in the Red Sea. That changed in 2023 with the discovery of widespread diffuse venting at Hatiba Mons, the largest axial volcano in the Red Sea. The vent fields there consist of iron oxyhydroxide mounds, are associated with thriving microbial communities, and are larger and more abundant than those previously known from any other ultra-slow-spreading ridge. The paper also noted that the Red Sea's warm, saline bottom water and limited connectivity to the wider ridge system may help explain why these vent communities look unusual compared with more familiar hydrothermal sites elsewhere. This is one of those findings that sounds thrilling in a press release and deeply significant in a research context. It means scientists are still discovering first-of-their-kind systems in one of the most strategically important seas on Earth. That discovery also sharpened a longer-running concern. Hatiba Mons sits in a basin where seafloor spreading is active, where exposed oceanic crust in some sections is geologically young, and where hydrothermal venting now has direct observational support. The 2023 study emphasised recent magmatic activity, fresh basaltic glasses, and lava flows likely younger than about 1,000 years. So when scientists keep finding new things in the Red Sea, they are not only filling in old gaps, they're documenting an environment that remains tectonically and hydrothermally active in the present. That gives every discovery a slightly different tone. A fossil system is one thing, a still working system is another. The Red Sea has a habit of turning out to be the second kind. The surface and shallower ecosystems bring a different sort of modern fear, because here the Red Sea has often looked like a rare source of hope. The northern Red Sea, especially the Gulf of Aqaba, has been discussed for years as a potential coral refuge under climate change. The logic was appealing. These corals appeared unusually tolerant of high temperatures, perhaps because of selection during their post-glacial recolonization history, and for some time the northern basin seemed able to avoid the mass bleaching seen in many other reef regions. Even recent work continues to describe the cooler northern Red Sea as a refuge candidate, while noting that central and southern Red Sea reefs already show slower coral growth and bleaching under warming stress. That combination, promise in the north and damage farther south, is part of what makes the basin so closely watched. Scientists are trying to understand whether the Red Sea contains one of the world's last coral strongholds, or merely one that fails later than the rest. The more recent findings make that question harder rather than easier. A 2025 study on 4 years of intensifying marine heat waves in the Gulf of Aqaba said explicitly that, despite warming faster than the global average, the region has been regarded as a thermal refuge for corals. Meanwhile, a 2026 study on mesophotic corals in the northern Red Sea reported pronounced species and depth-specific impacts of heat stress on coral physiology, and showed accelerated warming across intermediate to upper mesophotic depths over the last 20 years. That is an important shift in tone. It does not erase the idea of refuge, but it complicates it. A refuge is not the same thing as immunity. The Red Sea keeps forcing scientists to replace neat labels with longer, less comforting sentences. There is a pattern to this. Again and again, researchers arrive hoping the Red Sea will fit into one of two categories. Either it is a uniquely resilient system that can teach the world how marine life survives climate stress, or it is an early warning sign of what warming, deoxygenation, and salinity pressure can do to an already marginal sea. What scientists keep finding is that it is both at once. Studies of coral health in the northern Red Sea note that climate change in this basin is progressing faster than the global average, that salinities can exceed 40 in the north, and that the system's unusual biodiversity and endemism exist under precisely the conditions that make it highly sensitive to further change. In other words, resilience here is real, but so is exposure. The very factors that have shaped hardy local communities may also leave them with little room to spare. This tension between resilience and limit is one reason the Red Sea feels so modern in its implications. Scientists are no longer only finding exotic phenomena there, they are finding useful analogues for the future of the oceans. The Hatiba Mons vent paper pointed out that deep Red Sea bottom waters are saltier and around 18 degrees Celsius warmer than most deep oceans, making the basin a possible analogue for earlier Earth conditions and a unique testbed for how life functions in warm saline deep water. The same paper noted that the deep Red Sea may simulate conditions more similar to Precambrian oceans than most present-day marine basins. That means researchers studying the sea are often looking backward and forward at the same time. They see traces of ancient environmental structure, but they also see a living marine system operating under heat and salinity levels that may become increasingly relevant elsewhere. Even the language scientists use around oxygen now reflects that concern. The Red Sea is inherently warm and saline, which makes its waters naturally lower in oxygen than colder marine basins. A recent report quoting Red Sea researchers warned that this baseline leaves the region especially vulnerable to further oxygen decline when heat waves or algal blooms increase biological oxygen demand. The exact phrase used was that the Red Sea is inherently low in oxygen because of its warm waters and high salinity, and therefore vulnerable to further declines. This is not a headline about a hypothetical sea somewhere else. It is about a basin already living close to several physiological thresholds. The Red Sea does not need to become exotic in the future. It is already operating under conditions that make additional stress a very serious matter. And while climate pressure gets most of the attention, scientists keep finding more ordinary signs of trouble as well. A 2024 study of Red Sea coral reef sediments reported increasing trace metal concentrations since the 1970s in at least some areas tied to warming and industrialization. The paper described Red Sea coral reefs as susceptible to ocean warming and trace metal pollution, with spatial differences across the basin, but a clear message that local human pressure and broader climate stress are arriving together rather than separately. This matters because the Red Sea is often discussed as though its greatest risks come only from grand geological or climatic processes. In reality, the familiar human ones are present too. Development, pollution, and coastal alteration do not wait politely outside while tectonics and marine heat waves finish speaking. There is a deeper reason these findings land so heavily. The Red Sea keeps revealing that past stress and present stress do not guarantee the same outcome. Deep water corals appear to have persisted through major glacial restriction. Some northern reefs still show unusual heat tolerance. Extremophile microbes flourish in brine pools and vent fields that sound almost custom-built to eliminate them. Yet none of that means the system is safe. Survival under one set of extremes does not automatically prepare an ecosystem for every combination of warming, pollution, oxygen decline, development, and biological disturbance that the modern century can produce. Scientists know this, which is why so much of the tone around the Red Sea has shifted from admiration alone to admiration paired with caution. A resilient system can still be pushed too far. Sometimes resilience is exactly what tempts people to assume they have more time than they really do. And then there is the simple fact that the discoveries keep coming. New brine pools in the Gulf of Aqaba, newly confirmed vent fields at Hatiba Mons, new genomic work at Red Sea vents and brines, new evidence from pore waters and sediment cores, new physiological studies on coral vulnerability. The pace of finding itself is part of the unease. Usually when a marine basin has been so central to trade, history and regional identity for so long, people imagine its major surprises must already be behind it. The Red Sea keeps proving otherwise. It remains even now underexplored in key ways. The gaps in knowledge are not decorative little gaps around the edges. They are gaps that can still hold first discoveries. That is not the sign of a simple sea. It is the sign of a sea that continues to outpace the stories people tell about it. That is why modern fears around the Red Sea do not come only from danger in the obvious sense. They come from recognition. Scientists are recognizing how much of the basin's present behavior is tied to deep history. how many of its apparent strengths come bundled with fragility, and how many of its most valuable clues also point toward larger planetary problems. Ancient waters are telling modern stories there. A glacial survival record raises new questions about resilience. A pristine deep archive reveals coastal hazard history along a developing shoreline. Warm saline deep waters and active hydrothermal systems provide windows into early Earth and possible future oceans. Corals that looked like a refuge now reveal species-specific vulnerability under continued warming. The Red Sea keeps offering findings that are scientifically rich and emotionally awkward in exactly the same moment. And perhaps that is the real source of the fear. It is not that scientists are discovering one dramatic catastrophe waiting in the dark. It is that they keep finding a system that behaves like a preview. Not a perfect preview, not a simple one, but a sea in which heat, salinity, isolation, tectonic activity, biological adaptation, and environmental stress all meet in ways that feel increasingly relevant beyond its own shores. The deeper the record goes, the more clearly it begins to suggest that the Red Sea is not merely a strange place on the map. It is a place where the planet rehearses some of its harder lessons a little early, which is why the next step in this journey is difficult to avoid, because once a sea starts looking like a preview, it also starts looking like a mirror. What makes the Red Sea especially difficult to shake from the mind is not only that it is strange now, it is that so many of the conditions scientists worry about for the future ocean are already present there in some form. It is warm by marine standards, it is salty because evaporation is high, rainfall is low, and river input is almost absent. It is semi-enclosed, which limits exchange with the wider Indian Ocean through the narrow Bab el-Mandeb Strait. It contains ecosystems that have learned to live near environmental edges most seas do not approach so consistently. In that sense, the Red Sea is not simply a place with unusual local problems. It is a natural laboratory for what happens when heat, salinity, isolation, and oxygen stress begin working together in one basin. That is why scientists increasingly treat it as a kind of mirror, not a perfect one, but a revealing one, showing how parts of the planet's marine future may look when multiple pressures stop arriving one at a time and begin arriving together. The first reason for that mirror effect is temperature. The Red Sea has been warming faster than the global average, and that fact has been recognised for years. A 2017 basin-scale study found an overall warming rate of about 0.17 degrees Celsius per decade, with the northern Red Sea warming by roughly 0.40 to 0.45 degrees Celsius per decade, exceeding global ocean warming rates. More recent work on Red Sea coral health summarised the concern even more bluntly, noting that the rate of projected sea surface warming is about 2.5 times higher in the Red Sea than the global average. Scientists do not find that important merely because hotter water is uncomfortable for marine organisms, though it certainly is. They find it important because warming changes everything else as well. It alters stratification, oxygen solubility, metabolic demand, coral bleaching risk, and the pace at which heat waves become ecologically disruptive. In a sea that is already warm, extra heat does not arrive as a mild inconvenience. It arrives as a narrowing of options. That narrowing is part of why the Red Sea so often appears in conversations about climate refugees and their limits. For years, the Gulf of Aqaba in the northern Red Sea has been held up as one of the most promising potential refugees for corals under global warming. The basic argument is that these corals may have inherited unusual thermal tolerance during their post-glacial recolonization history, and several studies have supported the idea that they can endure temperatures substantially above their usual summer maxima. The notion has not disappeared. In fact, a 2025 study reported that corals in the Gulf of Aqaba survived 4 consecutive and intensifying marine heat waves, including an exceptional 2024 event that lasted 113 days, reached 32.6 degrees Celsius, and accumulated 30-degree heating weeks, described there as the highest recorded globally during 2024. The monitored colonies persisted without bleaching, and one 2025 Nature paper still described the northern Red Sea as generally considered a thermal refuge. That would sound like reassuring news if the Red Sea were only meant to reassure us. It is not, because the same refuge story keeps arriving with footnotes. The 2025 Gulf of Aqaba heatwave study showed remarkable resilience, but it did not show identical responses across all corals. Some species remained metabolically stable, while others showed significant symbiont reduction before recovering later. Other recent writing on the northern Red Sea has stressed that the refuge idea is debated precisely because this is a landlocked or semi-enclosed sea with extreme sensitivity to changing environmental conditions. The concern is not that the corals there are weak, it is that even a strong system can be misread if people mistake resilience for immunity. A place that survives a record heatwave can still be living in a region that is warming rapidly, accumulating stress, and depending on biological margins that are not infinitely elastic. When scientists look at the Red Sea and call it a refuge, they often do so with a tone that says, quite clearly, for now perhaps. That same double message, resilience and risk together, makes the Red Sea feel like a preview of how future oceans may be discussed elsewhere. In many parts of the world, the language of marine science is shifting away from simple categories. Habitats are no longer just safe or unsafe, recovering or collapsing, tolerant or fragile. They're often all of these at different times under different combinations of stress. The Red Sea already lives in that more complicated vocabulary. Its northern reefs may show unusual tolerance. Its central and southern reefs are more vulnerable to bleaching and heat stress. A 2025 coral regionalization study and a 2025 citizen photo analysis both point to this basin-scale unevenness, with central Red Sea sites suffering major bleaching-related cover decline and not appearing to function as climate refugia in the way some farther northern reefs might. That unevenness is exactly the kind of thing scientists expect more of in a warming world. Not one uniform outcome, but a patchwork of winners, losers, temporary holds, delayed failures, and local surprises. The Red Sea also mirrors the future because warming there is not acting alone. Climate models assessed for the basin project substantial 21st century sea surface warming, around 3.3 plus or minus 0.6 degrees Celsius under a high emission scenario, and about 1.6 plus or minus 0.4 degrees Celsius under a more moderate scenario by the end of the century. The same work projected strong increases in marine heatwave intensity and cumulative heat stress, with especially severe changes in the southern Red Sea. That matters because marine ecosystems do not respond only to average conditions, they respond to extremes, to duration, to repeated insults, and to whether there is enough recovery time between one event and the next. The Red Sea is already giving scientists a place where future-style heatwave regimes can be studied in a basin that remains ecologically rich but physically constrained. It is one thing to model that future in abstract. It is another to watch pieces of it already happening in a real sea. Then there is oxygen, which is where the Red Sea becomes a particularly sharp mirror for what many marine scientists fear most in coming decades. Warmer water holds less oxygen. Stronger stratification can reduce ventilation. Organisms living in hotter water often need more oxygen metabolically, while finding less of it available. The Red Sea is especially useful and unsettling here because it is already warm and saline enough to be naturally prone to low oxygen stress. In 2025, researchers documented 2 subsurface oxygen-depleted zones in deep depressions of the Differt-Ferguson carbonate platform, one suboxic and one effectively near anoxic, with oxygen below detection in the more severe case. They argued that the Red Sea's warm saline waters and semi-enclosed geomorphology restrict vertical mixing and limit oxygen resupply at depth. The wider point is hard to miss. Scientists often talk about future tropical coastal systems becoming more vulnerable to oxygen depletion. The Red Sea has already started producing localized versions of that future. What makes those oxygen-depleted depressions especially revealing is that they are not sterile dead zones in the simplistic sense. The study reported resistant aerobically respiring taxa and even fish under very low oxygen and high temperature conditions, showing an unusual capacity to reduce aerobic oxygen demand at temperatures above 21 degrees Celsius. That detail matters because it reveals, once again, the Red Sea's favourite lesson. Stress does not automatically erase life, but it does reorganise it. Future oceans may not simply lose ecosystems in a clean, dramatic sweep. They may instead force species to compress their niches, alter their metabolisms, and occupy increasingly strained states that still function, but at a cost. The Red Sea is already showing how that might look. A system can remain alive and still be under pressure severe enough to make scientists distinctly uneasy. Salinity is another part of the mirror, and it is one that does not always get the same attention as temperature, even though it shapes the entire basin. In the northern Red Sea, salinity commonly exceeds 40. That is high enough to become a defining ecological condition rather than a minor background detail. The basin's high evaporation, negligible precipitation, and absence of riverine input are exactly the sort of hydrological features expected to matter more as climate change intensifies the water cycle in many subtropical regions. Scientists already recognize that shifts in salinity can alter physiology, species distributions, and ecosystem structure, and the Red Sea provides a full-scale marine example of what long-term life under high salinity looks like. It is not a perfect analogue for every other ocean basin, of course, because very few places have its exact geometry and heat balance. But it is an invaluable natural case of what happens when marine life is asked to cope with warmth and salt together rather than separately. Even the deep Red Sea seems to belong more to tomorrow's concerns than yesterday's assumptions. The basin's bottom waters are warmer and saltier than those of most deep oceans, and the recently confirmed hydrothermal vent fields at Hatiba Mons sit beneath water masses that are already about 18 degrees Celsius, warmer than typical global deep ocean conditions. The vent field study explicitly suggests the deep Red Sea may function as an analogue for ancient oceans, and as a natural setting for understanding how life and geochemistry behave under warm, saline deep water conditions. That makes the basin scientifically precious. It also makes it a little unnerving, because many climate discussions now centre on compound stresses rather than single ones. The Red Sea is already a compound stressor sea. Heat, salinity, restricted exchange, tectonic activity, hydrothermal chemistry, oxygen stress, and biological adaptation are not separate chapters there. They are all taking place in the same water body at the same time. There is a broader climate lesson in that. Ocean change is increasingly understood not as one smooth trend, but as a set of interacting pressures. Warming changes oxygen. Oxygen changes metabolism. Stratification changes nutrient delivery. Salinity changes osmotic stress. Extreme events compress recovery windows. Local pollution, habitat degradation, and coastal development pile on top of the large-scale physics. The Red Sea is one of the places where those interactions are easiest to see in one basin. Its corals face warming and heat waves. Its deep depressions reveal localized deoxygenation. Its brine pools show what happens when salinity and chemistry go to extremes. Its hydrothermal vents add another layer of environmental stress. A global 2025 Nature climate change study emphasized that ocean stresses such as warming, acidification, deoxygenation, and salinity variation increasingly act together and reach deeply into the water column. The Red Sea is not just compatible with that picture, it feels like one of its most vivid regional examples. And yet, this is where the mirror becomes awkward rather than tidy, because the Red Sea does not simply reflect collapse, it reflects adaptation too. Scientists keep returning to it because it offers something rare, a chance to study systems that have already been living near environmental thresholds for a very long time. Some organisms there may hold lessons about tolerance, acclimatization, or evolutionary filtering that could matter far beyond the basin. The Gulf of Acaba's corals, for instance, remain among the most important test cases in the world for understanding whether some reef systems can persist longer under global heating than expected. The deep brines and vent systems do something similar for microbial ecology and biogeochemistry. If the future ocean will be harsher, then the Red Sea may show not only what gets damaged first, but also what kinds of biological strategies remain possible under sustained stress. Scientists are drawn to that knowledge for obvious reasons. They're also wary of how easily it can be misunderstood. A few resilient lineages do not cancel a basin-wide problem. There is also a human dimension to why this mirror matters so much. The Red Sea is not some remote, lightly used natural experiment. It is one of the world's major shipping corridors. Its coastlines are being developed rapidly in places. Its reefs support tourism, fisheries, and regional livelihoods. Its waters matter to multiple nations at once. So when scientists say it may reflect the future of the planet's oceans, they're not speaking about an abstract model aquarium tucked away from consequence. They are speaking about a sea where ecological stress and human dependence are tightly braided together. The same pattern is likely to become more common globally. Climate pressure will matter most where natural systems are already complex, already crowded by human use, and already operating near environmental thresholds. The Red Sea fits that description almost too well. What makes all of this especially difficult is that the Red Sea keeps refusing the comfort of a single moral. It does not tell scientists that all reefs are doomed, because some of its reefs keep resisting. It does not tell them resilience will save everything, because parts of the basin are already bleaching, warming rapidly, or carrying other signs of stress. It does not say deoxygenation is a distant future problem, because localized oxygen poor zones are already present. It does not say extreme marine conditions are incompatible with life, because its deep brines and hydrothermal sites are full of specialized organisms. The sea keeps saying something more complicated instead. The future ocean may be harsher, patchier, more selective, and more biologically strange than most people expect. Some systems will endure, some will fail. Many will do both in different ways before the story is over. That, in the end, is why the Red Sea feels so much like a mirror. It does not reflect a neat cinematic disaster. It reflects a world in which stress arrives unevenly, where biology improvises under pressure, where local refuges exist but cannot be romanticized too quickly, and where a beautiful sea can also function as an early warning system. Scientists look into it and see not only reefs, rifts, brines, and hot deep water. They see the outlines of a more demanding oceanic future, already taking shape in one narrow basin between Africa and Arabia. And once a sea begins to feel like that, once it starts behaving like both a refuge and a rehearsal, the line between wonder and warning becomes very thin indeed, which is where the next part naturally begins. That thin line becomes harder to ignore the longer one looks at the Red Sea, because this is one of those rare places where wonder does not sit safely on one side and warning on the other. They occupy the same water, the same basin that holds some of the most biologically distinctive coral reefs in the world, is also a basin warming rapidly, accumulating stress and forcing scientists to think very carefully about how long beauty can remain stable when the background conditions keep shifting. The Red Sea is a globally significant hotspot of coral reef biodiversity, and official regional conservation documents describe it as one of the most valuable repositories of marine biodiversity on the planet, with more than 265 coral species, around 800 fish species in the Saudi Red Sea and Gulf of Aqaba context, and unusually high endemism in parts of the basin. At the same time, those same sources frame it as a place whose value depends on urgent conservation, because its uniqueness also makes it irreplaceable. That is the first reason the Red Sea sits so uncomfortably in the scientific imagination. If it were merely damaged, the story would be grim but simple. If it were merely beautiful, the story would be pleasant but less urgent. Instead, it is both extraordinary and exposed. International Coral Reef Initiative materials from 2024 describe the Red Sea and Gulf of Aden coral systems as covering about 13,605 square kilometres, around 5.3% of the global coral reef area. while also supporting food, livelihoods and tourism for millions of people along the coastline. In other words, this is not a decorative ecosystem tucked away from human consequence. It is ecologically rich, economically important, and regionally indispensable, which means any warning sign here lands with more force than it would in a place no one depended on. Part of the wonder is obvious even before science becomes involved. The Red Sea contains clear water, steep reef walls, vast fringing reef systems, and a combination of tropical biodiversity with unusually arid coastal settings that gives it a character unlike many other reef provinces. UNESCO's description of the Gulf of Aqaba and the Saudi Red Sea emphasizes this combination of rich marine biodiversity, deep water close to shore, high salinity, steep topography, and ecosystem services that make the area socially and economically important. Those same features also help explain why the region can feel so scientifically compelling. It is not a standard reef sea. It is a reef sea with drop-offs, deep basins, brine pools, thermal extremes, and a narrow connection to the wider ocean, all of which make it feel less like a single ecosystem and more like several overlapping experiments running in the same place. Still, the wonder on its own is not what keeps researchers awake. What does that is the growing realization that the Red Sea may be one of the clearest examples of how a marine system can look strong and precarious at the same time. In the northern Red Sea and the Gulf of Aqaba, corals have repeatedly drawn attention for exceptional thermal tolerance. UNESCO's Red Sea nomination materials summarize a large body of work showing that some of these corals appear exceptionally resistant to heat stress, and may represent one of the world's most important natural laboratories for studying coral adaptation to climate change. The Gulf of Aqaba has therefore often been described as a potential refuge. That is the hopeful part of the story, and it is not trivial hope. If some coral systems really can withstand temperatures that would kill close relatives elsewhere, then scientists need to understand that as fully as possible. But refuge is one of those words that sounds safer than it is. A 2025 study on 4 years of intensifying marine heat waves in the Gulf of Aqaba reported that tagged colonies from 5 coral species survived 4 consecutive heat waves, including the extreme 2024 event, without mass bleaching. The same paper described 2024 as reaching 30-degree heating weeks, the highest during the global bleaching event that year, while still finding exceptional resilience in those corals. That sounds almost miraculous by current reef standards, and to some extent it is. Yet even that study showed species-specific metabolic responses rather than uniform invulnerability. Some corals stayed more stable than others, some changed and then recovered. The lesson is not that the Red Sea is safe. It is that some parts of it are buying time in ways scientists are still trying to understand. This is where the warning begins to move closer. Marine heat waves are increasing, and the Red Sea is warming fast enough that many of the region's most hopeful findings are now accompanied by a kind of careful scientific hesitation. Older basin scale work already showed the northern Red Sea warming faster than global ocean averages, and more recent assessments continue to warn that projected sea surface warming in the basin is high, and marine heat waves are expected to intensify. A 2025 Nature Communications study on marine heat wave drivers in the Red Sea concluded that regional atmospheric forcing and circulation patterns are shaping these events in different parts of the basin, reinforcing the idea that future stress will not arrive as one simple, uniform blanket of heat. It will come unevenly through local combinations of air-sea forcing and oceanic transport, which is often harder for ecosystems to handle than a single tidy trend line. The central and southern Red Sea make this even harder to romanticize. Research on subsurface marine heat waves showed that focusing only on sea surface temperature can miss biologically important warming lower in the water column. That study linked an unprecedented coral bleaching event in the southern Red Sea in 2015 to subsurface heat stress, despite less dramatic surface signatures than another event in 2002. This matters because it removes one more layer of comfort. Even when the surface does not appear to be screaming, the water beneath may still be quietly cooking sensitive reef communities. The Red Sea, once again, refuses to let the easy version of the story survive for very long. Then there is the matter of oxygen, which rarely gets the same public attention as coral bleaching, but has a talent for becoming quietly serious. The Red Sea is inherently warm and saline, and those two traits alone reduce oxygen availability compared with colder basins. In 2025, scientists documented subsurface oxygen-depleted zones in depressions of the Diffout-Ferrison carbonate platform, with one of them effectively near anoxic. The explanation they offered was straightforward and not especially comforting. Warm saline waters, restricted vertical mixing, and the sea's semi-enclosed geometry can limit oxygen resupply at depth. That means the Red Sea is already capable of producing localized low oxygen conditions that resemble the kind of deoxygenation risk scientists expect to become more common in a warming world. The future, in this basin, is often not future tense. And yet even here, the sea continues to complicate the message. Those oxygen-poor zones did not prove to be clean, empty voids. The researchers found evidence that some aerobic taxa and even fish were persisting under very low oxygen in relatively warm conditions, suggesting that life can compress itself into unexpectedly difficult states. That is the Red Sea's favourite kind of lesson. A warning appears, then an adaptation appears beside it. A stressor intensifies, then a specialised community finds a way to function within it. Scientists are not soothed by that. They're intrigued and worried at once, because adaptive capacity is real, but so are thresholds, and one does not necessarily tell you where the other ends. Human pressure sharpens that uncertainty further. An Earth System science data paper from 2024, summarising field data and context for the Saudi coastal Red Sea, lists a broad set of pollution drivers along the coast, including maritime transport, fisheries, aquaculture, oil, gas and energy infrastructure, coastal industry, tourism, municipal and industrial discharge, and urban development. That is a remarkably crowded list for a sea already coping with natural heat and salinity extremes. It means the Red Sea is not merely a climate story, or merely a tectonic story. It is also a very ordinary human use story, complete with shipping corridors, wastewater, coastal alteration, and competing economic ambitions. Nature brought enough complications. We have apparently decided to contribute some of our own. The deep sea is not exempt from this either. A 2025 study of deep sea marine litter off Al-Waj in the Saudi Red Sea found that plastic was the only observed macro litter type in their survey area, and that distribution patterns were influenced by geomorphology and hydrography, with debris accumulating in submarine canyons and topographic depressions. The authors linked much of this litter to maritime traffic. That is a small detail in one sense, but it carries an uncomfortable symbolic weight. Even the parts of the Red Sea that look like dark remote geology lessons are still receiving the leftovers of global shipping and modern waste streams. The basin's topography collects our evidence nearly as effectively as it collects its own sediments. Research patterns themselves hint at the same tension. A 2024 review of Red Sea coral reef research called The Basin, a globally significant hotspot of coral reef biodiversity, and analysed more than 1,600 publications, while also showing how unevenly reef science has been distributed in space and theme. That suggests something quietly important. The Red Sea is famous, ecologically important, and scientifically productive, yet it remains incompletely covered, with some locations and topics receiving much more attention than others. A place can be admired, intensively studied, and still only partially understood. In the Red Sea, wonder keeps drawing attention, but warning keeps reminding everyone that attention has not yet become comprehension. That incomplete understanding is part of why conservation language around the Red Sea often sounds unusually earnest. UNESCO's documentation describes the region not only as spectacular and biodiverse, but as home to what it calls the world's only genetic assembly of climate-resistant corals in the northern sector, arguing that these corals cannot simply be preserved in laboratories because their value lies in the living ecological system itself. Whether one adopts that exact wording or not, the point behind it is clear enough. Some of what makes the Red Sea precious cannot be separated from place. You cannot peel off a few genes, store them in a freezer, and declare the problem solved. The reefs, currents, thermal history, connectivity, and local ecological relationships matter together. That makes the line between wonder and warning especially thin, because every sign of exceptional biological value becomes, at the same time, an argument for protection. There is another reason this line is so thin. Wonder encourages attention, but it can also encourage optimism beyond the evidence. A sea full of resilient corals, endemic fishes, deep brines, hot vents, and unusual ecological thresholds can start to feel invincible in the imagination. The science does not support that conclusion. Even the optimistic refuge framing used in official and scientific discussions comes with caveats about local disturbance, basin-scale warming, bleaching in other Red Sea sectors, and the need for active protection. The 2024 ICRI Forum material, for example, celebrated the Red Sea's importance for global coral conservation, while framing current efforts explicitly around building future reef resilience in a rapidly changing ocean. That wording matters. You do not talk about building resilience when you believe a system is beyond concern. You talk that way when you know the concern is already real. Perhaps the clearest expression of the Red Sea's split identity is this. It remains one of the few marine regions that can still offer genuine hope to coral science, while simultaneously offering evidence of the same stresses threatening reefs worldwide. It can present exceptional thermal tolerance in one area and bleaching sensitivity in another. It can hold rich biodiversity, endemism, and fisheries value, while also showing pollution drivers, deep litter accumulation, oxygen decline in depressions, and intensifying heatwave risk. It can serve as a scientific refuge and a scientific warning in the same paper trail. That does not make it contradictory. It makes it honest. Real ecosystems under modern pressure rarely give us the courtesy of a single mood, so the Red Sea sits there, beautiful enough to make people assume everything must be fine, unusual enough to keep researchers fascinated, and stressed enough to make them cautious every time they praise it. It is a place where admiration has to travel with restraint. Scientists can marvel at reefs that resist heat, at endemic species, at deep basins that preserve hazard records, and at life surviving in hostile chemistry. They can do all of that honestly. They just cannot do it casually anymore. Too much evidence now points to a basin where the most astonishing features are also the ones most likely to matter in a harsher century. That is why the line between wonder and warning has become so thin here, not because the Red Sea has stopped being extraordinary, but because it remains extraordinary under conditions that increasingly look like a test, and that leaves only one gentle step before the close of this journey, because after all the reefs, brines, heat, depth, and buried history, what lingers is not only what scientists have found, but what it feels like to know that this sea is still keeping more than we have managed to read. And so, dear listener, we find ourselves near the edge of this long and careful journey, not at the end of certainty, because the Red Sea does not hand that out very often, but at the end of what we can say for tonight, without needing another vessel, another set of sensors, and probably another very patient team of scientists staring into the dark. We began with a sea that seemed almost too beautiful to be troubling. We drifted past old trade routes and empires that learned, sometimes expensively, that narrow water can still be far bigger than human ambition. We moved below the bright surface into brine pools, heat, fracture, hidden fire, and life that seems to have negotiated private agreements with chemistry itself. And now, after all of that, the simplest truth may be the one that lingers best. The Red Sea is frightening to scientists not because it is chaotic, but because it is so precise. Everything about it means something. The salt means something. The heat means something. The deep basins, the oxygen-poor pockets, the reefs that resist and the reefs that struggle, the sediments that keep old records, the predators waiting at the edges of lethal water, the microbes turning impossible conditions into daily routine. All of it means something. This is not one of those natural places that merely looks dramatic. It is one of those places where each layer keeps proving relevant to the next. A tectonic rift shapes the seafloor shapes the pools shape the chemistry shapes the life shapes the record, and the record shapes the questions scientists ask about the future of oceans far beyond this one narrow sea. That, perhaps, is why the silence of the Red Sea feels so heavy once you know what lies beneath it. On the surface there are waves, coral gardens, coastlines, ferries, cargo ships and sunlight. There is life in the way most people understand life. There is motion in the ordinary human sense. But lower down, where the light fades and the water presses from all sides, another kind of silence takes over. It is not empty silence. It is loaded silence. It is the silence of dense brine holding its boundary, the silence of sediment settling into a place where few creatures will disturb it, the silence of hydrothermal warmth rising through rock and salt, the silence of microbes carrying on with ancient chemical work in total darkness, the silence of a system that does not need to announce what it is doing because it has been doing it for longer than our species has had language. There is something deeply humbling about that. Human beings do like to imagine that mystery shrinks neatly when science arrives. We picture the old darkness giving way to clean explanation, like turning on a lamp in a room and discovering that everything is exactly where it ought to be. But some places do not behave that way. Some places become stranger the more carefully we look at them. The Red Sea has been doing exactly that. Each new instrument has sharpened the picture, but it has not made the place smaller. It has made it larger. Each answer has connected the sea to wider processes, to plate tectonics, climate stress, deep time survival, future ocean conditions, and the biological limits of endurance. The unknown has not disappeared. It has become more organised, which is in some ways even more unsettling. Scientists know this feeling well. It is the feeling of reaching a point where the evidence is no longer thin enough to dismiss, but not thick enough to make anyone comfortable. The Red Sea has entered that category in a serious way. We know enough now to say it is one of the most unusual marine basins on Earth. We know enough to say that parts of it preserve records other places lose. We know enough to say that some of its ecosystems may help us understand how marine life responds to heat, salinity, and oxygen stress. We know enough to say that some of its coral systems appear unusually resilient while others are already showing signs of strain. We know enough to say that its deep brines and hydrothermal structures are not side notes but core features of how the basin works. And we know enough to recognise that all of this makes the Red Sea more than a regional curiosity. It makes it important in a way that is difficult to overstate. Still, importance is not the same as mastery. It never has been. The Red Sea has a long history of reminding people that usefulness does not equal control. Empires learned that when they tried to bend it into a route. Modern science is learning a quieter version of the same lesson now. We can map, measure, sample, sequence, and model. We can lower cameras into the dark and recover cores from seabeds that look as though they should have shredded the paperwork before we arrived. We can learn a great deal, but the sea keeps enough of itself to remain ahead of us. That is not a failure of science. It is one of the reasons science matters. A place that still resists easy summary is a place still worth listening to. And the Red Sea does feel, in its own way, like something that must be listened to rather than conquered. That may sound gentler than the facts deserve, but gentleness and seriousness are not enemies. A sleeping mind can still hold a hard truth. In this case, the truth is that the Red Sea has become one of those places where beauty and warning are no longer separate categories. Its reefs are not merely lovely reefs, they are test cases. Its deep brine pools are not merely exotic features, they are archives, chemical extremes and ecological traps. Its warm water is not simply warm water, it is data, pressure, and in some parts of the basin a forecast. To look at the Red Sea now is to look at a sea that has become scientifically double-sided. Admiration lives on one side, concern lives on the other, and the paper between them is getting thin. There is also, I think, a very human reason the Red Sea stays with people after the research papers are closed and the vessel decks are quiet. It is because this sea keeps exposing a gap between what we assume a place is and what it really contains. From shore it can seem almost simple, from above it can seem manageable. Even its name, dramatic though it is, does not prepare anyone properly for what lies below. Then the layers begin. Heat where there should be cold. Salinity where there should be dilution. Life where there should be only harshness. Records where there should be disturbance. Vulnerability where there should, by appearances, be confidence. The Red Sea is a reminder that reality is often arranged beneath appearance rather than inside it. That is true in geology. It is true in biology. It is true in history. And perhaps it is one of the reasons stories like this can feel so calming and so unsettling at the same time. They ask us to admit that the world is deeper than the glance we first gave it. For scientists, that depth is both privilege and burden. To understand a place like the Red Sea is to gain access to extraordinary information. It is also to inherit responsibility for what that information suggests. One does not study a sea like this and walk away with the comfortable impression that oceans are endlessly forgiving. The Red Sea teaches almost the opposite. It shows resilience, yes, but it also shows boundaries. It shows adaptation, but also selectivity. It shows how life can survive astonishing conditions, but not without cost, and not without limits that may become visible only when it is too late to be casual. This is one of the harder lessons in environmental science. The existence of endurance is not permission for neglect. Sometimes resilience is simply the last clear sign that a system has been under pressure for a very long time, and that is why so many of the questions still waiting in the Red Sea feel larger than the basin itself. Scientists are not only asking what lives in the brines, or how a vent field formed, or how a coral species responds to a particular heat wave. They're also asking what future marine systems may look like when multiple pressures arrive together. They're asking how much stress an ecosystem can absorb before its outward composure stops meaning anything useful. They are asking what survival looks like in a warming, increasingly strained ocean, and whether the places we call refugees are truly safe or simply slower to fail. The Red Sea does not answer these questions neatly. It only insists that they are worth asking. There is a kind of comfort in that, oddly enough. Not comfort in the sense that the problems disappear, because they do not. More in the sense that careful attention remains possible. The world is full of systems so large and tangled that they can make a person feel helpless if viewed all at once. The Red Sea certainly has that quality, but science, at its best, is a practice of returning to complexity without flinching. It is the act of saying, "This is difficult, and still we will look closer." A core sample is taken, a profile is run, a reef is surveyed, a microbial genome is assembled, a sediment layer is read, a hidden pool is found. Knowledge grows in increments. It may not arrive with the speed of a dramatic revelation, but it arrives all the same, and sometimes those careful increments are the difference between vague unease and real understanding. Even so, understanding has a habit of making the world feel more alive rather than less. Before we knew about the deep Red Sea brines, the sea was already important. Before hydrothermal venting was directly observed there, the basin was already unusual. Before scientists traced coral resilience and heat stress across its regions, the reefs were already beautiful. What knowledge has done is not remove the mystery, it has shifted it. The mystery is no longer what could possibly be there. It is, how can all of this be there at once, and what does it mean for everything else? That is a more mature kind of mystery perhaps, less theatrical, more demanding, the kind that lingers after the lights are off. And maybe that is the right note for a closing like this. Not finality exactly, but lingering. The Red Sea does not feel like a place that should be wrapped up too neatly. A tidy conclusion would almost insult it. Better to leave it as it is. A sea bordered by desert and history. A sea whose reefs gleam in shallow light, while its deepest basins hold hot brine, strange life and old evidence in the dark. A sea where the crust is still opening, where warmth already pushes living things toward their limits, where records of earlier disturbance remain preserved below, and where every discovery seems to sharpen the outlines of the next unanswered question. So tonight, as this journey slows and the water grows still again, perhaps the best way to leave the Red Sea is not with an answer, but with an image. Imagine the surface at night, calm enough to reflect almost nothing. Imagine the depth below it, layered and hidden, carrying salt, heat, sediments, microbes, waiting predators, resilient corals, buried history, and all the careful concern of the scientists who keep returning. Imagine how little of that is visible from above, and then imagine how often the Earth works like that. How often the quietest places are doing the most complicated things. How often the most beautiful surfaces cover systems still under strain, still in motion, still writing their own records in darkness. If this voyage brought you some calm, some curiosity, or just a quieter end to the day, I would be ever so grateful if you liked the video, subscribed, and stayed with me for the next gentle descent into another corner of the world that seems simple until it very much isn't. It helps this little space reach more people who enjoy falling asleep somewhere between science, wonder, and the slow, steady rhythm of learning. And if your thoughts are already beginning to drift, then perhaps this is a good place to let them go. Because for all our measurements and maps, the Red Sea remains what it has always been. A body of water that gives us enough to keep going, and keeps enough to itself to remain worthy of return. The silence is still there. The depth is still there. The questions are still waiting. And somewhere below the last of the light, in water too warm, too salty, too strange, and too revealing to be forgotten, the sea is still keeping its own counsel. Sleep well, wherever you are,